Hi, it's time for another math easy solution, and today I'm going to go over further into vector functions, and this time look at arc length and curvature. And yeah, before we go further, just a note, as always, you could, if you don't have time to watch this whole video, you could play this video at a faster speed. And top secret life hack, your brain gets used to faster speed. And here is a tutorial I made on how to do so, and with the browser extension there that you can download. And also you can download and read the notes in PDF format. Link will be in the description below, as well as reading the notes in article format on the Hive blockchain. And you could also watch a video in parts, and timestamps of all parts are in the description as well. And I'll also be making a video sections playlist of short clips of this entire video, and I'll be uploading those gradually. All right, so let's go further. And again, with the timestamps, you could skip straight into the start of the video. So anyways, going further, it's a calculus book reference. So note that I mainly follow along the book Calculus Early Transcendental 7th edition by James Stewart. There's a link to that. And I used the following solution manual for this chapter, and there's a link to that. And again, these will be in the notes or article format on the Hive blockchain. And also note, in some earlier videos, I used the 6th edition. There's a link to that one. All right, let's go further. So calculus book chapters, the Hive notes and sections playlist for each video of this chapter are listed below. So you can go to vector functions, there's a full playlist, and then each chapter has its there's the notes there on the Hive blockchain, as well as the full sections playlist, and the full video is in there as well. And then the current one is arc length and curvature, and there's a playlist for that, and I'll be uploading those as finished video and so on. And also and these links will also be on the MES links webpage, mes.fm/links, so check that out. All right, going further, so topics to cover. Note that the timestamps will be included in the video description for each topic listed below. So we'll go over arc length, and then we'll go over example 1, arc length of circular helix. And then we'll look at parameterizations and arc length function. Then we'll look at example 2, which is arc length function of a helix. And then we'll look at curvature, definition of curvature. Example 3, curvature of a circle is 1 divided by the radius. So we'll show that. And theorem, curvature, cross product formula. We'll go over example 4, curvature of a twisted cubic. Example 5, curvature of a parabola. And then the normal and binormal vectors. Example 6, unit normal and binormal vectors of a circular helix. And then the T and B frame, that's basically tangent, normal, and binormal frame. Normal, and then we'll look at normal osculating planes. Then example 7, normal and osculating plane of the circular helix, which is actually the example 6 helix. And then look at osculating circle, and then example 8, osculating circle of a parabola. All right, now that we dived all the way into that, so now let's take a look at arc length and curvature, the chapter, and the first part is on arc length. All right, so in my earlier video, we defined the length of a plane curve with parametric equations x equals f of t, y equals g of t, and then where t, the parameter t is between a and b, as the limit of lengths of inscribed polygons. And for the case where the derivative f prime and g prime are continuous, we arrived at the formula. And here I'll just write this one out. So this was the formula. Then I'll go over a recap on arc length, the videos I had in a bit. But here's the formula we got to: integral from a to b. And this would be again for a plane curve with parametric equation. And this is going to be in 2D. Again, it's going to be f prime of t, like this, squared, and I'll remove the square root. We'll add it all further out in a bit, but then the next one's going to be g prime of t squared, like that, and then this is going to be all square root like this, and then dt, and then this equals to, you could also write it as the integral from a to b of, then there's again the integral, put it like this, I mean the square root dx over dt. So again, it's the same thing as dx over dt. Is the f prime. This one's correlating to the x coordinate, and this is squared, and this one is to the y component, and derivative with the parameter t. And this is going to be, I'll put it like this, dy over dt. and then dt like that. That's the same thing. All right, so this was the formula, but now let's do a quick recap. So first recall my video on arc length of a curve on y equals fx. So this is just the basic one, not the parametric equation one. So if we have y equals f of x like this is the blue curve. So yes, that's the blue curve like that. And so if we have something like that, and then basically what we do is separate these up into, these are the polygons it's talking about like this. Like that in this case is just like, yeah, this is polygon, four-sided one. And then basically you draw a line between each one, and then you would sum all these up to get the full arc length, and limit as this goes to infinite amount, that's closer and closer. And also if you zoom into each one of these, instead of using a straight line, again, you could split those up into many different ones. If that's the actual curve, this is a straight line like that, or you could do something like this, if you break them down infinitely like that. Yes, again, if you just, instead of just using this bigger one, you could use smaller and smaller one, you can get something like this. It would be more accurate. So anyways, so the limit as, so the full arc length right here, like that, is the limit as you have infinite of these polygons. So instead of this big, you may have it like really small, and so on. And then, yeah, so the limit as this difference goes to 0, or you have an infinite amount. So limit as the n approaches infinity of the summation from I equals 1 to n of the, and then you just sum up all the distances, pi 1 to pi. And yeah, this one here, from this to here, this one is just zoomed in. Think of the way calculus book was basically saying if you can just split these up even further. But anyways, that's the whole idea. And then the derivation, it obtained this one, the arc length formula. If f prime is continuous on a and b, then the length of the curve y equals fx, where x is between a and b, is going to be this limit right here. Yeah, and this limit is this equals integral from a to b of square root 1 plus, and then f prime of x squared, and then dx. And in fact, this is actually the same thing as this one here. This is f and t. This because you're using parametric equations here. In this case here, it's just taking the derivative of x is just 1. So this actually here, so this one could be viewed as dy over dx. Because remember right here, this is just dx over dt, this is dy over dt. But if you're doing it in terms of x, this would be dy over dx. This right here could be viewed as just dx over dx. And dx over dx just cancels, equals 1. Yes, equals 1. Yeah, and here I just fixed it up because I wanted to add this because later this will actually come up in one of the examples, and this is just squared like that. Just put it for completeness so that doesn't look like we're taking the whole thing. Anyways, so now going further, so now recall my later video on arc length and parametric equations. This was just a basic function. Now we're taking parametric equations, and again, when you have parametric equations, you basically use the parameter t as opposed to making it as a function of x. So you're going to have both the y and the x as functions of t. So you're going to have some weird curves like this. Whereas the other one, you have one-to-one functions and so on. So anyways, it goes like this. So if you have the, right here, if the curve c is described by the parametric equations x equals f of t, y equals g of t, and then where t is between alpha and beta, and then where f prime and g prime are continuous on the interval on a of, from alpha to beta, and c is traversed exactly once as t increases from alpha to beta. So let's say it's starting from here. Yeah, it goes like that exactly once. Doesn't go many times. Doesn't go back and forth or infinite amount of times in a loop. Going further, then the length c is just going to be this right here. This was again from earlier video. You can go see the proof for that. So L equals to integral from alpha to beta of square root dx over dt squared plus dy over dt squared dt. Yeah, so that's what we have there. And again, this corresponds to this one right here. But when you're dealing with just y equals f of x, this part here, dx over dx is just 1. Yeah. So anyways, going further. Yeah, so the length of a space curve, and now the difference, those were 2D, now we're doing 3D. So remember, recall my earlier video, so on basic space curves. So space curve is defined in exactly the same way in see figure below. So what I'll do here is, let's say we had in 3 dimensions, so we're going to have a y, z, and this is going to be x coordinates there. So let's say we had, and this is the origin. So let's say we had a space curve that goes like this, goes like that, and then it cuts in like this. and goes around like that, or goes behind. Actually, I just fixed that up. I had the calculus book actually had the other way around, so that this had the looping from the back and then going into the front. Like that. So let's say we have that, and let's add the now let's change the color here. So we're going to be doing the exact same way. So arc length, we're going to be doing exactly the same thing. We're going to take a point like this. We're going to basically draw a bunch of lines like this. This would go like somewhere. Let's go Control Z. Yeah, this goes something like this, and this would go like this. This would go like this, and then this would go like this. This would go like that. Again, the exact same thing. I'm just exaggerating for. Yeah, just for just showing it. Yeah, so you have something like that. And what I'm actually going to do is I'm going to just erase this. This is and the reason of that is because I'm just going to use the screenshot there. So you get the idea. I'm just going to use a screenshot because it looked much nicer. So there's a screenshot from my calculus book. So again, you get the idea. It just goes like that. So if my drawing isn't as good, I'm just going to use the calculus book one because it's just, again, much better. But you get the idea. So again, you just do the exact same thing. So suppose that the curve has the vector equation r of t is equal to, now in 3 dimensions, f of t, g of t, and h of t, where t is between a and b, or equivalently, the parametric equations x equals f of t, y equals g of t, z equals h of t, where f prime, g prime, and h prime are continuous. So if the curve is traversed exactly once, as t increases from a to b, then it can be shown that its length is, and I'm not going to prove it in this one just because calculus book didn't prove it. I might prove it in a future video, but we'll see about that. Yeah, but it's going to be, again, we're going to get pretty much the exact same as expected setup there. And I'll change this, change this back to black and close this. So we're going to have L, and then you already know how it's going to be. It's going to be integral from a to b. This is the arc length. It's going to be the square root. And we're probably gonna have a bigger square root, but anyways, let's keep it like that. F prime of t squared plus g prime of t squared plus, and then h prime of t squared, like that. And then cover all that up, dt. And now this equals 2. Again, you could write in the other format, integral from a to b, and this is going to be like this. Instead of writing it like this, we'll write dx over dt. This is the x component, dx over dt squared plus, and now g is the y component. Let's erase this. This is going to be dy over dt squared plus dz over dt squared, and then this is dt, like that. And now notice that that both of the arc length formulas above can be put into the more compact form. And yeah, that's this formula right here, or you can consider both, and then this one here as well for the parametric. I mean the 2D one is the plane curve, and the other one is the space curve. So 3D, this is 2D. These are just distance formulas. Yeah. This is just this is the formula from point A, to just point B. Yeah, so in other words, it's just a distance of a vector, and this right here, yeah, this is just the length of the vector with components at those points, and I'll just write this out. Oh, but this is the derivative of it. So this is going to be L in compact form. We could write this as the integral from A to B of the distance of the derivative, or the length of the derivative vector. This is going to be r, you have vector function r prime of t, like that, dt. Yeah, so that's all it is. And yeah, this is because for plane curves, so if we have a plane curve, r prime of t is equal to f of t I plus g of t j. So those are the components. Then what we'll have is the distance of the derivative. So then we're going to have r prime, the absolute value or the length of it, or the magnitude. Yeah, this means magnitude or the length of it. This equals 2, and then we take the derivative of the components, and then we also take the this is just going to be, I'll just put it for completeness, f prime of t I plus g prime, and this is the magnitude of that g prime of t j component, or the xy component. And now this equals 2, well, the distance, this is the length of the vector function, like that. That's going to be now, this is going to be f prime of t squared, yet square root of all that plus, and then this is going to be g prime of t squared, like that. Like this. All right. Yeah, and for space curves, there's basically 3D curves. What we end up having is, well, we have that extra z component, so h of t there. So it's the exact same thing, but we have an h of t there. This is going to be now, this is going to be the length or the magnitude of the derivative of the vector function r is going to be equal to, and then this is going to be the, again, magnitude, same thing as f prime of t I, I'll erase this, I, vector, so that's the standard basis vector, and then this is going to be g now, g prime of t, j, plus, and then this is going to be h, t, and then this is going to be k, like that. Now this equals to, yeah, same thing, so just take the full square root, and this is going to be f prime of t squared plus g prime of t squared plus h prime of t squared, like that. All right, like this. I'll just square this squared better, like that. Yeah, so that's what we have. And yeah, now quickly just recall here's a link to my earlier video. So recall the distance formula in 3D and 2D. All right, and here I just quickly paused the video and basically just added the thumbnail instead. So if you have distance again in 2D or 3D, and again you could the 2D just has the z component gone. So you could think of it as just applying the square root or the Pythagoras twice there. So if you have a point from this point P1 all the way to P2, so P1 to P2, like that. Yeah, so I'll just make an arrow like that from there to there. And then basically, yeah, you're going to take the square root of the differences of each component squared, add those all up, and then square root, that's the distance from here to here. Yeah, that's going to be, that's actually quite fascinating. And you could, again, the square root that arises from the Pythagoras theorem there when you get the hypotenuse, but now you do it a second time. Once you get this, you do the second time to get that. So anyways, that's distance from in 3D or 2D when you just vanish the z component. Anyways, let's continue further. And we're asked here, example 1, arc length of circular helix. So find the length of the arc of the circular helix. Yeah, with vector equation r of t is equal to cosine t, I plus sine t, j vector plus t k vector, or basis vector. Anyways, from the point 1, 0, 0 to the point 1, 0, 2 pi. So in other words, one thing to notice here, this is the z component, this is z component, this is z component. So in other words, it's saying from t, this is t, equals 0 to t equals to 2 pi. So basically we're going from the parameter t equals 0 to t equals 2 pi. So solution, so since r prime of t, so we'll take the derivative of this, r prime of t, because we're going to need the r prime of t. Remember, we're going to basically take the distance is going to be this. So integral from a to b, or from 0 to 2 pi of the length of the derivative of the vector function. Or vector equation or vector function. Anyways, it's going to be cosine, derivative of cosine t, recall that, just going to be negative sine t. I, and then derivative of cosine t is just going to be cosine t j, and the derivative of t is just 1 with respect to t. Yeah, so t is just 1, so just put k vector like that. Yeah, so since that, so we have, yeah, so now what we get is the length r, yeah, the length of, or the magnitude of the derivative is going to equal 2, and we just take the square root and then square everything in each component. So we're going to take a negative sine t squared plus cosine squared t, and then this is going to be plus 1. 1 squared is just 1, so just leave it. I'll just put it for completeness, and then later I won't do that as much. And this is going to be, well, this is just equals to the positive. This is going to be sine squared t, and then combine these two, sine squared t plus cosine squared t. That's just a Pythagorean, the trigonomic Pythagorean identity. and or Pythagorean identity. Pythagoras basically sine squared plus cos squared equals to 1. So that equals to 1. All right, that equals to 1. And so what we end up having is, yeah, this just equals to square root 1 plus 1. This is 1, square root 1 plus 1 equals to square root 2. So the length is square root 2. That's the actual arc length. That's quite amazing. Actually, whoops, no, that's not the arc length. That's just the length of the vector function. Now we need to take the derivative to get that. Okay, so that's the other thing. So that's basically we need to take the derivative from that was just the in between. Yes, derivative from a to b. So now we use the arc length formula. So derivative. The integral from a to b of the length of that vector function, which was square root 2. So let's put it in. All right. So the arc from 1, 0, 0 to 1, 0, 2 pi is described by the parameter interval 0. Where t is between 0 and 2 pi. Again, because this is the x component, z component. That's z. T is 0, and then goes to 2 pi. So from this point to this point. So basically from that parameter. And so from the compact arc length formula we have, so the arc length now is equal to actually this one here. Integral from a to b, or 0 to 2 pi of this length. Derivative length of the derivative of the vector. Like that. Dt, which equals to the integral of from 0 to 2 pi of square root 2 dt. And this is just standard integral calculus. This equals to, this part right here will equal to integral of square root 2. That's just a constant, so it's just going to be t. So we'll take the 2 out. This is going to be now, this is going to be t. Yeah, t from 0 to 2 pi. Yeah, and we just plug this inside. Well, this is going to be 2 pi minus 0, so this just equals to, well, I'll put this as a, I'll put this like this, square root 2 times 2 pi, and then the calculus book writes it like this, puts a 2 in front, square root 2, and then put the pi over there. That's what the calculus book does it, and that's what we have. And going further, we can actually calculate this out. So note that 2 times square root 2, and this is because my OneNote has a built-in calculator, so I have to write it like this, or you could just put it in the power of 1/2. But anyways, if you could just write 2 times square root 2 times pi, and this equals to, well, I'll put this like this, space equals space, and automatically calculates it. So it's built-in calculator, and this is roughly, this is 8.8857. You could round it up to 8.89, so this rounds up to 8.9. So this 5, this 7 goes to 6, this goes to 9. Yeah, so you could round it up like that. So, and now the figure below shows the arc of the helix whose length is computed in example 1. This is from a calculus book. It looks like this. So this is a circular helix. The starting point is 1, 0, 0. So there's the on the x component, and then it's a circular helix. It goes around like that, and goes all the way to 1, 0, 2 pi, and then where this length is to 2 pi. I'm just using the calculus book screenshot just because I'm not going to go and try to graph it. You can do that yourself. But here, for reference, here's the drawing in the GeoGebra 3D graphing calculator. Or here is the curve, the helix. Yeah, so I use the graphing calculator right here. So if you go to GeoGebra, you could write curve, helix equals curve, and then I just put that in cosine t, sine t, then t, and then where the parameter is t. And then from 0, basically the way you write it is now 0 to 2 pi. And then you plug, then basically it looks like this. And 2 pi is going to be 6.28 or 3.14 times 2. And then this is cosine t, sine t, and t. And there's also a length function. So you can actually just write length of the helix from 0 to 2 pi, and it goes 8.89. Exactly this. Absolutely fascinating. And then also the points 1, 0, 0, and then points 1, 0, 2 pi, or just to graph it out, and it looks like this. So there it is, exactly it. And this one, I think just these units are a bit, the scale's different from the x and y, but you can adjust those as you see fit. So what I'm going to do is go right here. So here's the curve, and again, you can play around with this like that, and you can see this. Yeah, so 6.28. You can increase that if you want to make it even more. And then I think if I press shift, if I press shift, I can change the scale. So now it looks more circular like that. And let's just play around to see what happens if I do, instead of doing 2 pi, we'll go to 10 pi. Yeah, so now you have a circular helix, goes all the way up like that. Yeah, and it goes, yeah, quite amazing. Yeah, and you can play around with that. And again, points fit in right there. There's the point A over there, and that length is 8.89. Quite fascinating. Again, you could just plug that in. So yeah, so our thing is, we double checked it and it's correct. If the calculus book is correct, we're correct. All right, and now let's go further and look at parameterizations and arc length function. So a single curve C can be represented by more than one vector function. And for instance, the twisted cubic. So if we have a twisted cubic from our earlier video I did a while ago. So if we have the vector function r1 of t, this equals to, this is going to be t squared and then t cubed, like that. And this is where t is between 1 and negative 1 and 2. And yeah, this twisted cubic can also be represented by the function. And what we'll do is I'm going to change a variable to u. And to do that, well, in this case, what I'll do is I'll just let t is equal to e to the u. And the reason we're doing that is because, well, it's easy to manipulate. Because if we take the natural log of both sides, we get a ln t equals to ln e to the power of u. And again, using basic natural log rules, the u goes down. And then we get a ln e, and then ln e is just equal to 1. So then we're just going to get a u equals ln t. So in other words, we get a u equals to ln of t. And now what happens is we're going to get a new vector function, but again, it's equivalent. This is called a parameterization or reparameterization of it. So r of 2, now we're going to be in terms of u, so it's a function of u. So it's a function of u, so we're going to take the exact same one, but now replace it with this equivalent e to the u. So t, instead of t, we get e to the u. Yeah, so this is going to be e to the u. And then t squared is going to be, well, e to the 2u. And then the t cubed is going to be e to the 3u. And now this is going to be between, well, u, we're doing it between u, and u equals ln t. So, and then where t is maximum is at 2, so ln 2 is less than ln 2. And it's greater than, well, ln 1. And I'll just put actually 0. And the reason it's 0 is because this is just whenever log of 1 is just going to be equals to 0. So this is just equals to ln of 1. Yeah, ln of 1 equals 0. So ln 1 equals 0 because the number t is the smallest one there. And then this is ln 2. Yeah, so it goes like that. Yeah, so that is the parameterization of that. And yeah, here, so this is from my calculus book where the connection between the parameters t and u is given by t equals e to the u. Yeah, I just added this. They just gave the answer, but anyways, just for completeness, just included their text. So we say that the above equations are parameterizations of the curve C. So you get this pretty much same thing. If we were to use the compact arc length formula or equation to compute the length of C using the above two equations, we would get the exact same answer. So again, I'm not going to do that, but you guys can go test it out, and you're going to get the exact same answer. If you were to take the arc length from of this twisted cubic or this parameterization, you're going to get exactly the same thing. So in general, it could be shown that when the compact equation is used to compute the arc length, the answer is independent of the parameterization that is used. And again, that's for proof for another day. Calculus book didn't prove it. I might do it later, but it's pretty straightforward. So now we suppose that C is a curve given by a vector function, and let's say we have this right here. This is the basic one, r of t equals 2f of ti plus g of tj, just a basic one, plus h of tk, like that. And then this is where t is between b and a, like that. Yeah, and where r prime is continuous, so the derivative is continuous, and c is traversed exactly once as t increases from a to b, then we define its arc length function s. So as opposed to the full arc length, we're doing an s up to a certain point t. And we'll call this s of t. So now this is going to equal to the integral from a to t. So as opposed to going from a to b, the full arc length, we're going to go a subsection, so a to t. And then that means we're going to have to change the variable inside. I'll do this. This is going to be now the derivative of using that compact equation. So our derivative of r, so r prime, and now we're going to put a u there just for the integral. I mean, and then this is going to be du, like that. And now this equals to the integral from, so from a to t of, now this is going to be, we'll do the giant like that, a square root. And now we're taking the derivative of dx over dt. Same thing, I mean du now, because we're doing, we're going to plug in the t after, once we take the full integral, squared. So we're just doing a change of variable, dy over du squared plus dz over du squared, and then all dt. Like that. All right. And whoops, it's not dt, du. Yeah, so it's all du, and then the only t is over here, because that's, we plug that in after when we evaluate, and so that's why it's still a function of t there. So anyways, yeah, so thus s of t is the length of the part of C, the curve C, between r of a and r of t vectors there. So see figure below. So if we had to use in 3D like this, let's see if I can make it good. If I make it good, I'll keep it. If not, I'll use the screenshot from the calculus book. So anyways, we have this like that. So let's say our starting point is here. This is going to be our r vector of a. And let's say the other one is right here. This is our z component. This is going to be, let's say, our r of t. Yeah, that's r of t. But let's say the full vector, let's just say the full one goes like this. Like this. Goes, it goes in a circle like that. Goes all the way across. Actually, I'll make this a bit better. Let's say, this part like this. And then this goes around, or behind it. All right, it goes like that. So let's say it goes like that. And I'm going to go and change the color now to red. So let's say we had this component. Yeah, so this is the curve there. Yeah, so this is between there and there. Yeah, between this and this part right here. This is t, yeah. And then it connects over to there and goes. So this would be the subsection. This would be our s of t. Like that. So that's our s of t. And then whereas the full one all the way to b would be, so the full arc length will be all the way to b. Yes, that's what we have. That's pretty cool. But again, I think I like the calculus book one a bit better. So what I'll do is I'm just going to erase this. It's good to just draw it out just to see it, how it's created. And I'm just going to erase this. Just because the calculus book one is quite good. So we erase that. And I'm going to erase this. And just, it's a bit better. So yeah, there it is. So again, so that's pretty epic calculus book setup there. Yeah, so we have the curve loops around, and then only just take this section there, and that's going to be our s of t. Anyways, going further, so if we differentiate both sides of the above equation using part 1 of the fundamental theorem of calculus we obtain. So if we take the integral of both sides to get the definite integral. No, actually, no, we're not taking an integral. Yeah, I mean, we're doing a differentiating. So that using part 1 of the fundamental theorem, we're not getting a definite integral. We're just getting the term inside. So if we take the derivative of this, ds over dt, this just means the derivative of that is just going to be, well, this inside there. That's just going to be that inside function there. So in other words, so then we obtain ds over dt is equal to, so again, this is just the derivative is going to be that internal function inside the integral. So r prime of t. So the derivative of the arc length function is just going to equal to the length of the second derivative of that function. So it's of the vector function. That's quite fascinating. And now for reference, just again, here's recall my earlier videos on part 1 and part 2 of the fundamental theorem of calculus. So again, screenshots from my calculus book, but the links are to my videos. So the fundamental theorem of calculus part 1, if f is continuous on a and b, then the function g is defined by the g of x equal to integral from a to x of f of t dt, and where x is between a and b. So this is the integral from a to x, and is continuous on a and b and differential on a and b. And then basically what we have is the derivative of this is equal to f of t, or now in terms of x now. So just put x there. So g prime of x is equal to f of x. So in other words, yeah, that's what we get. Yeah. So and now if the fundamental theorem of calculus part 2 is if f is continuous on a and b, then the integral of f(x) dx is equal to, well, the antiderivative. So if you take the derivative of these, you get f there is equal to f of b minus f of a. So where f is any antiderivative of f, that is a function such that the derivative of capital F is equal to f. So the fundamental theorem of calculus basically summarizes: suppose f is continuous on a and b. If g of x is equal to integral from a to x f of t dt, then this right here, g prime of x equals fx. So in other words, in our case, the s prime is equal to the r prime of t. That's this part right here. So the derivative of this is equal to this. Again, that's just part one of the fundamental theorem of calculus. And then the second part, integral from a to b, fx dx equals f of b minus f of a, the capital F of a minus f of, capital F of b minus f of a, where f is any antiderivative of f, that is derivative of capital F is equal to f. So that's pretty epic. So it is often useful to parameterize a curve with respect to arc length, because arc length arises naturally from the shape of the curve and does not depend on a particular coordinate system. Now, that's interesting. So if you're using one coordinate system and it's not that it's complex, you can just change it to another one and just get the same answer. So that's pretty fascinating. So if a curve r of t is already given in terms of a parameter t, so if a curve is already given it, and s of t is the arc length function given by the above equation. By the above equation for s of t, so this one right here. So if it's already given by this one here, that's s of t, then we may be able to solve for t as a function of s. So we can actually solve for t as a function of the arc length function. So in other words, we can write t as a function. So t is equal to a function of the arc length, of the arc length function there. That's pretty fascinating. So s there. So then the curve can be reparameterized in terms of s for t. So if you have the vector function r, you could write this as equaling to r of, instead of r of t, so now it's r of t of s, where t is a function of s. And then plug that inside. So then we get the same thing, but it might be easier depending on the situation. So thus, if s equals 3, for instance, r t of 3 is the position vector of the point 3 units of length along the curve from its starting point. So basically what this means is if you had a curve now, I'll draw this one. The calculus book didn't actually draw one here, so you're getting a unique drawing right here. So y, this is z, this is x. So let's say we had our starting vector is going to be at this point r of t of 0. I'll write r prime of t of 0, like that. So the length is 0, so at this starting point there. So it goes like this, and this is our curve C, and then we go all the way to here. This is going to be r of t of 3, and this is, again, that's the arc length function. So in other words, that means that this distance, and I'll draw this out in red actually. I'll draw this out in red. This right here, this distance, this is equal to s equals to 3. So basically this is the vector, position vector at a distance 3 from the starting point. So that's a quite interesting way to put it. All right, I'll close these. All right, and now going further, let's take a look at example 2. It's the arc length function of a helix. So we're asked reparameterize the helix r of t equals cosine ti plus sine ti j plus tk with respect to arc length measured from the point 1, 0, 0 in the direction of increasing t. And so a solution, the initial point 1, 0, 0 corresponds to parameter t equals to 0. That's because, again, the t right here is the z component. The z component here is 0, so t is 0. And also recall from example 1, this is actually just example 1. So we scroll all the way back to example 1. We had a circular helix. Let's take a look at that's this part right here, example 1. So we had the circular helix from the point 1, 0, 0 to all the way to 1, 0, 2 pi. And we showed that the arc length is, the length of the second derivative is going to be square root of 2. And the full arc length is 2 times square root 2 pi. And if you scroll all the way back down here, and I just copy and paste it from calculus book. And here from example 1, we basically have the length of the arc length is equal to integral from 0 to 2 pi, and then of the integrand is going to be the second or the first derivative of the vector, so r of t, the length of it, and then that equals to integral from 0 to pi of, this was the length of the derivative, square root 2, and then take the full integral. So the full arc length from 0 to 2 pi is equal to 2 times square root 2 times pi, which was about 8.89. But anyways, but in our case, we're going to go from up to t. So we wanted to go up to t, and we already solved interesting. So we have this as integrand using the part 1 of the fundamental theorem of calculus. Well, we already know that the derivative of s, so the arc length function, ds over dt is equal to that integrand. So the length of the derivative of r of t. So this, in other words, we already know this part right here is equal to ds over dt. Yeah, this is just ds over dt. Yeah, so that's just that part. So I'll just write, so we'll go like this, ds over dt is equal to the length of the derivative of r, which equals to, in our case, square root 2. This equals square root 2. Yeah, so and now we could just do basic integrals. So what we get is, well, we can move this t over to the other side, and we're just going to get a ds, just for completeness, put it like that, and differential form or whatnot, and then take the integral on both sides. So what we get is, and this is integral from 0 to t. Yeah, we'll just take integral from both sides. We're gonna go to 0 to t. So, but then we're gonna change a variable there. But anyways, so what we'll get is, I'll just put it like this: 0 to t, or I'll put that actually here. So we're gonna go integral from 0 to t ds. This equals to integral from 0 to t, and now this is square root 2, and then this just needs to be du, just to change the variable so that we plug the t after. And now this is integral, again for completeness, this ds, integral of ds is just going to be s, and then put the t in there, s of 0 is 0, the length is 0, so anyways it's going to be s of t is equal to 0 to t square root 2 du, and then this just equals 2, just basic, this is just a constant, so this is just going to be a constant, so we just leave it out and go from t, and then from 0 to 2, from t. So this just equals to square root 2 times t. Yeah, so what we get is, well, we get s is equal to, I'll put this like this, s equals 2 square root 2t, or you could write this as t is equal to s over square root 2, because if we're going to reprimarize this like that, yeah, so we have t equals to as a function of s, so that's pretty fascinating, s over square root 2. So thus the required reprimariization is obtained by substituting for t equals this one, and again that's to get this whole idea where we have r of t of s, so we have r of t of s, like that. That's how we reprimarize it in terms of s for t. So what we're going to get is, well, we're going to plug this all in. So we're going to get r of t of s. This equals 2, and we need to replace all of that with it. So we go back to our function. We have this right here. So cosine t is going to be now cosine, what was it, s over square root 2. And then sine will be, s over square root 2. And then t is s over square root 2. So this equals 2. Cosine, and now this is going to be of s over square root 2 I plus sine of s over, fix this up, square root 2, yeah, it's moved it around, make some room, and then j, and then plus s over square root 2 k, like that. Yeah, so fascinating. All right, and now let's continue further, and this time look at curvature. So a parameterization r of t, so this vector function r of t is called smooth on an interval I if its derivative r prime is continuous and that the derivative for all values of t is not equal to 0 on I. And a curve is called smooth if it has a smooth parameterization. And again, what this all means is basically a smooth curve has no sharp corners or cusps. And when the tangent turns, it does so continuously. So there's nothing sharp about it, and so on and so forth. So if C is a smooth curve defined by the vector function R, recall that the unit tangent vector from our earlier video, so this is capital T of T, is given by, this is just, and I'll recap quickly from our earlier video, this is equal to, and as the unit tangent vector is going to be the derivative of the vector function divided by the length of the vector function. So R prime of T, the length or magnitude below. So that you divide by it, so that you basically make this all just, this length is going to be 1, or the unit tangent vector, like that. And this indicates the direction of the curve. So recall from an earlier video on unit tangent vectors, there's a link over there. And then there is a thumbnail. Again, I pride myself in the thumbnails. So here's the curve right here, C. So you have the curve like that, and at this point P is where the position vector R of T is, and this defines basically the curve for any values of T. So and if you increment by H right here, you get the you go up to Q, and then this difference right here, R of T plus H minus R of T, that's this right here. And then if you just multiply by 1 over H, that's a scalar, so it's not going to change the direction. This is parallel to that one. And the reason we do that is basically we take using the definition of derivative of a vector function. So then dr over dt is equal to the derivative of this position vector there, or this curve there, this vector function, equals to the limit as h approaches 0, and then the difference r of t plus h minus r of t divided by h. So basically the limit of the secant vector as h approaches 0, and then basically you get this right here, and it gets closer and closer to this curve, and that's the direction of the curve. So this is pointing this way, and that's the r of t. And then the unit tangent vector is, you just divide this by the length. So you divide this by the length. So what you end up getting is somewhere like that. This would be like t. This would be t. Like this little thing would be t. Yeah. So just divide by that. If this one is bigger than 1. Anyways. Yeah, so that's a recap from that. So now from the figure below, you can see that the unit tangent vector, capital T of T, changes direction very slowly when T is fairly straight, but it changes direction more quickly when C bends or twists more sharply. All right, so I'll draw this out, and I'm probably gonna show the screenshot of the calculus book after, because it's a bit hard drawing in 3D neatly. Just to get the point. So basically, if we have a curve like this, so this is the 0 there, this is the x, and if we have a curve like this, all right, so let's say this is our curve C, and then, all right, and then here I just moved it over to have some space, and now we get the red marker there. So now we're going to draw the unit tangent vector. So when it's straight, it's not going to change much. It's going to be like still like that, and these are the unit tangent vectors, basically the direction of the curve and of increasing T. And then, but as it curves, you can see there's these big changes now. Now it's going to be pointing like this. It's going to be pointing, I think, like something like that. And now, as it goes up, curves up, it goes from down to up. This one's just up and up, and then it curves like that. So this is again what the unit tangent vector which will show, and it's always the same length, magnitude 1. That's why you're dividing by the full length there. Okay, so it's going to be like that, and so on. Yeah, it's going to be like that. So it's pretty good stuff there. And again, I'll just take a screenshot from my calculus book. So yeah, you get the idea. I like drawing it out just so you can follow along. But now here's a screenshot again, much nicer. So it's the unit tangent vectors at equally spaced points on C. So yes, epic stuff there. These are equally spaced points there, and that's how it looks like. There's the unit tangent vectors. And now, the curvature of C at a given point is a measure of how quickly the curve changes direction at that point. So yeah, so that's going to be on the curvature. These are the unit tangent vectors, and specifically we define this curvature, or we define it to be the magnitude of the rate of change of the unit tangent vector. So as this is being changing right here, basically the derivative of this unit tangent vector that signifies the curvature. So if this is a low amount of change, it's going to be low curvature. High amount, it's going to be high curvature. And we're going to also define it to be the magnitude of the rate of change of the unit tangent vector with respect to the arc length. So we're going to respect to the arc length, and the reason is we use arc length so that the curvature will be independent of the parameterization being used. So because you could use many different parameters for that curve, as we showed before here. Yeah, as I showed here, you can have the twisted cubic written in t. You could change a variable and so on, but the arc length is going to be the same regardless of which parameterization. So we're going to basically define curvature based on the arc length. So that's going to be very interesting. All right, so going further, so definition of curvature. So the curvature of a curve is, and this can be using the Greek letter kappa. So it's like that. It looks like K, but it's like a bit smaller and a bit slightly different looking. So this is going to be, the length is going to be dt, like that, over ds. Like that. And this is, yeah, the length of the derivative of the unit tangent vector with respect to the arc length as opposed to the parameter t. And actually, more specifically, this is the arc length function. So up to the parameter t. So again, that's ds. So remember, right here is the arc length function. Yeah, let's go right here. So this is the arc length function is from integral from a to t of the derivative of of the length of the derivative of the curve of the tangent vector. Yeah, basically, this is the tangent vector, length of the tangent vector. From a to t, as opposed to the full arc length from a to b. All right, so that's that one there. So again, that's the section right here. That's the arc length function, s of t. It's fascinating stuff. All right, and yeah, going back to definition right here again, where t is the capital T is the unit tangent vector, and again, just for completeness, to write it down as well. So note that this symbol kappa, or it looks like a K, is a Greek letter kappa and not just a normal K. Notice how it's slightly different. There, this one is a bit, this is a normal K. It starts from, this is below the center line. And then the normal other one is smaller, and it starts in the center line. So this is equal. Yeah, this is equal to this one. Yeah, so that's pretty fun. Interesting. Yeah, so that's how it looks like. So again, going further, so the curvature is easier to compute if it is expressed in terms of the parameter t instead of s. So we use the chain rule to write, or the chain rule for vector functions. And again, this is defined in terms of the arc length function because it will be independent of the parameterization, but we still want to express this same definition in terms of parameter t because it's easier to compute. So yes, we'll basically have to rewrite how this will look like. In terms of t, we want it in terms of t, but not in the definition. Just definition in terms of arc length. Now we convert this thing into parameter t. So to do that, we use a chain rule. So what we want is something, we'll start off with a derivative of the unit tangent vector in terms of the parameter t. So d of capital T over dt is equal to, and this is a function, so the arc length function is a function of t, of the parameter t. So we'll have to take the derivative of this d over, this is a d over capital T over ds, and then using chain rule, and then a chain rule derivative of ds over dt. So to do that, yeah, to convert it into parameter t, we need to use chain rule because this is a function of t anyways. So this, what we end up getting is, and now we have this, and now we're going to isolate this part right here, or by isolating it by moving this over to the other side. So we're going to get a d capital T over ds. Again, that's the inside function. That's what we want to convert. This is going to equal to now the left side. And what I'll do is I'll write this like this: d over, I'll just put a giant thingy like this: d over t, capital T over dt, divided by, and now this is going to be ds over dt, like that. All right, so what this means is, and I'll write and. Now we have our curvature, this kappa. Kappa is going to equal to, and then we just plug that inside there. So kappa is equal to, well, derivative, the magnitude of the derivative of the unit tangent vector in terms of the arc length function. I'll just put this for completeness: d capital T over ds. So now this equals to, well, this is going to be the magnitude of this giant fraction. So it's going to be the magnitude. And I'll try to make this more compact. So d over t dt, derivative like that, divided by ds over dt, and the magnitude of this whole thingy there. Like that. All right, so we have this, but we already know, but we know what ds over dt is. This right here, recall earlier, ds over dt, this equals 2, and if you just scroll back up, yes, let's scroll all the way back up to when we had the fundamental theorem of calculus. Again, when we took the arc length function right here, and then the derivative of that in terms of ds over dt, that is just equals to the integrand, or the term inside. So in other words, the derivative of the magnitude of the derivative of the vector function. So in other words, ds over dt equals to the magnitude of the derivative of r prime. Yes, r prime of t, like that. So that's what we get. So we'll just write that down. So now we can get rid of the s completely. So ds over dt equals to the magnitude of this right here, r prime of t, like that. All right, yeah, so now that we have that, so we could write, well, so, or thus, so basically what we get is this kappa, and we just plug this, we just plug that inside there, and this also d capital T over dt, that's just we could write that in just the other format, the prime format. So this equals 2, and I'll write this is going to be, the top part is going to be the magnitude of the d prime of t, so in terms of t, derivative, and this one's going to be divided by, and now ds over dt is equal to just this part right there. These are vector functions, so like that. So r prime of t, the magnitude of that. So yeah, that's what the curvature is in terms of t. So the derivative, the curvature in terms of s is just a derivative of the unit tangent vector, the magnitude of that. But then in terms of t, it would be the magnitude of the derivative in terms of t divided by the magnitude of the vector function itself, divided by, in terms of t, like that, derivative of that. So yes, fascinating stuff. Yeah, and actually, before we go further, I'm going to write this as in terms of t, like that. So that's the curvature in terms of t. All right, and going further, just to recap now, just from my earlier video for the chain rule for vector functions, so why we're able to do this. Basically, the chain rule for vector functions, it shows it's the same analog for regular functions, as for regular functions. So recall from earlier videos, here's a thumbnail of it, there's a link to that earlier video. So d over dt of, if you have a function within a function, it's a u of f of t. In our case, this is d of, this is derivative of the unit vector t dt over ds, where s is a function of t. So like that. Yes, in other words, the derivative of d over ds is a function of t, so we could take derivative of the inside function as opposed to s. So this is going to be, in our case, it was s over t. Yeah, so anyways, so d over u of f of t equals to the derivative of the inside. So we take the derivative of the inside, or chain rule, just take the derivative of the outside right now, first of all, in terms of the f function. And then you take the derivative of the inside, multiply that out. So again, using chain rule like that. And again, there's the setup there. There's actually the proof there as well. And you get this, you can just expand these out and use basic derivative chain rule for regular functions inside each component, and you get that. Anyways, let's go further. Well, let's take a look now at example 3. Curvature of a circle is 1 divided by radius. So that's fascinating. So show that the curvature of a circle of radius a is 1 over a. So basically show that the curvature of a circle is just 1 divided by the radius. So solution, we could take the circle to have the center, the origin, and then a parameterization. A parameterization is, and before we get to that, I'm going to just draw a circle like this. This is our x, this is our y. So we have x, y. Let me draw a big circle. And here, quickly pause the video and just added a circle like automatically from the thingy, because the OneNote, I mean the calculus book didn't actually have a drawing there, so we can't just, so I have to make this one pretty good. And here I'm just moving this around to make this a bit bigger. So I just use the built-in circle thingy from OneNote. Yeah, because we can't just rely on the screenshot of the calculus book in this case. So I'll make this even bigger so it's easier to view. I'll put it like that, right in the center. Like that. I'm just going to put it like that. And I'll move things around. All right, here I just added this like that, and the reason I'm doing this is just to recap on how to get the equation, parametric equations of a circle. And if you draw a triangle like that and using Pythagoras, so let's say our t starts from here. There's our t, and this is going to be, let's say this is going to be our x, this is going to be our y, and this is going to be our radius a, like that. And this is the point here at x, y, like that. And then as using just basic trigonometric function, so cosine of t is equal to the adjacent over hypotenuse, so x over a. So then we just move this a to the other side to get x, and likewise sine, so opposite over hypotenuse, is equal to y over a, and then move the a to the other side, and we get our sine ta, like that. Yeah, so it's fascinating stuff. Yeah, so that's what we get, and then basically what that means is we could write these in the components. So at the xy, so r of t, so the curve right here, I'll call this c, and yeah, c, and then this point right here, this is just our that's our hypotenuse a, but it's also our r vector of t, like that, and the length is going to be a, so that's the length or the radius there. So this is going to be r of t is equal to, and its components is going to be x and y. So I'll just put for completeness xi plus yj, and this equals to, well, x is going to be equal to, yeah, just for completeness, so the x, move it over to there, it's going to be a cosine t I plus a sine t j, like that. All right, so now that we have this r of t, well, the next setup is we need the curvature, right? So the curvature, we need to get r of t like that. Yeah, so we need to take the prime of it, I mean r prime, and we also need these t prime of t, like that. And again, this one is also dependent on the vector function derivative as well. So anyways, so let's just write this further. So thus what we get is r prime of t is equal to, well, derivative of this one, derivative of cosine, just negative sine. So this is going to be a sine t I, and then derivative of sine is just cosine, so plus a cosine t j, like that. All right, so we get that, and we need the length of it, or the just basically apply the distance formula. So we take the length, so so that's that, and the magnitude or the length r prime of t, this equals to, well, just using that square root and then the squares of the inside terms, it's going to be negative a sine t squared plus a cosine t squared, like that. All right, and going further, what this, let's just simplify this. Again, we're going to use that same Pythagorean identity and cancel out stuff. So basically, this is the minus, because we're squaring, it's going to be positive. The a is going to be an a squared, and then this also has an a squared there, so we just factor that out inside. So this equals to a squared, just factor that out. And then the next one's going to be, well, sine, sine squared is when cosine squared. Sine squared of t plus cosine squared of t, like that. And again, this is the basic Pythagorean identity. This equals to 1. So we're just left with square root a squared, and a square root a squared just equals to a, or plus or minus a. We're only dealing with positive values. So a, like that, is the value. All right, so we got this part here. That's the bottom part of this equation. And now we need the top part right there. So to do that, well, first we need the actual unit vector in terms of, basically, this is the derivative of it, but let's just get it first without the derivative and recall that one. And that's just unit tangent vector, just the derivative of the vector function divided by the length of the vector function. So this is this one right here, and then we need to take the derivative of that. So let's go write this down here. So we have this term. So I'll put this like this. Now not d. This is the vector function. The unit tangent vector function is equal to, and I'll put this in terms of t. Yeah, so in terms of t is equal to, this is going to be r prime of t divided by the length r prime. Yeah, the length of the derivative r prime of t, like that. All right, so this equals to, well, the bottom is going to be 1 over a. So let's put 1 over a like that. That's the bottom. And then times it by, so 1 over a times, and then times, well, the derivative is this part right here, negative a sine t, a cosine t. So negative a sine t plus cosine, plus a cosine t. And this is I, forgot to put the I. This is because it's a vector, so we have to put the components I plus, and now we're going to go plus a cosine t j, like that. Yeah, so that's what it is. And then the a's cancel. So a's just cancel. This is going to be equal to negative sine t I plus cosine t j, like that. All right, so we have this, and this gives, and writing this gives, because my calculus book wrote this gives, but anyways, this gives, now we take no, actually they wrote this gives afterwards, and this one here is, they wrote, yeah, so, or and, put it like this, and the derivative t prime of t is equal to, and now we just take the derivative of this. Well, derivative of sine is just going to be cosine, so negative cosine t I, and now the next one is going to be cosine. Well, derivative of cosine is negative sine t, so negative sine t j, like that. So fascinating stuff there. All right, and now I wrote, I wrote this gives, and also here I'm going to write so. Yeah, so that equals that, and now this gives, and now we take the length of this, so the length of this derivative of the unit tangent vector. This equals to, again, put this in a giant square root, and now this is negative cosine t, and this one that, and again, this just equals, so for a complete, I'll just put the negatives there, and then squared plus sine, negative sine t squared, like that. And again, this just becomes, well, again, that just equals to 1. Again, I'll just for completeness write the whole thing. The negatives become just positive because it's we got the square there. So now it's going to be cosine squared t plus sine squared t. And again, when we're dealing with circles, we're going to get that Pythagorean identity pretty much always. Yeah, so this terms equals to 1. So this whole thing equals to square root 1 equals to, well, plus or minus 1. We're only dealing with the positive distance value, so 1. Like that. Yeah, so now we have all the ingredients. All right, so thus, put it like this, thus, now kappa, the kappa in terms of t, is equal to, this is the curvature, this again, kappa now equals to, we already know this is going to be the length of the derivative of the unit tangent vector in terms of t divided by the length of the vector function derivative in terms of t. Yeah, so we just divide those out. So this is going to be capital T derivative, and its length derivative of this t, like that. And we put it like this. Okay, thus that over, and now the, like that, derivative of the vector function, the length, the magnitude of it, and the top part is equal to 1, so that's 1 equals to 1. The bottom equals to, well, a. So this is the bottom, the magnitude of the derivative of the vector function in terms of t, so a, so 1 over a. So there it is. We proved that it equals to, the curvature of a circle is 1 divided by the radius. Yeah, 1 divided by its own radius. So fascinating stuff there. So as a gets bigger, yeah, the curvature decreases. As a gets smaller, curvature increases as expected. All right, and here I wrote that down as well. So the result of example 3 shows that small circles have large curvature and large circles have small curvature in accordance with our intuition. Yeah, as smaller, when you're dividing by a smaller number, you're going to get a bigger number. And when you're dividing by a large number, a large radius or larger circles, you're going to have smaller number or smaller curvature. as expected. So we can see directly from the definition of curvature that the curvature of a straight line is always 0 because the tangent vector is constant. Yeah, and that's just looking from here, definition. This right here, the derivative is going to just equal to 0. So derivative of the unit tangent vector is going to be just horizontal. In other words, equals 0. So curvature is 0 of a straight line. Because tangent vector is constant. And although curvature formula, although the curvature formula can be used in all cases to compute the curvature, or actually, more specifically, although the curvature formula above, I forgot to put that there. So although this one right here, although this one you could use to use in all cases to compute the curvature, the formula given by the following theorem is often more convenient to apply, and this involves the cross product. So sometimes it's oftentimes it's more convenient as opposed to just using this one. You could use it all the time, but it just might be a bit harder because you gotta get all these terms and so on. And sometimes it's easier to use this one, which I'll go right here. So theorem, curvature, cross product formula. The curvature of the curve given by the vector function R is, and I'll write down here, this is gonna be kappa of t, so it's gonna be also in t. This equals 2, and now the magnitude or the length of the derivative of the vector function R of t cross product with the second derivative. So apparently according to my calculus book, this is easier to apply. So you take the derivative second time, and I can see why it would be, because you typically get simpler derivatives. Sometimes you do. So anyways, a simpler second derivative. So anyways, it's going to be now this part right here is going to, and then divided by the magnitude of the first derivative cubed. All right, so this is quite a fascinating formula right here. So this big giant one, or it's not that big and giant, but just seems bigger than this one here. It's actually easier oftentimes to compute than this one here. So let's continue further. All right, and now here what I'll do is I'll go over a proof of this. So here's the theorem, and now we're going to prove this actual cross product curvature formula. So to do that, we'll do is starting off with t. So let's go with the curvature. Not curvature, the unit tangent vector of t. Remember, this just equals to the derivative of the vector function at t divided by the unit length. The magnitude of the unit tangent vector, like that. And now, when we have this, I'm going to rearrange this in terms of the top part here, because we're going to have a lot of these derivatives. Derivatives of the vector function. So I'm going to go rearrange this. It's going to be, and then basically move the bottom over to this side. So this is going to be unit tangent. Not unit tangent. This is going to be the vector function derivative in terms of t equals 2, and put this one in front. So the length of that derivative multiplied by the unit tangent vector, like this, like that, t. This is just multiplied like that. All right, and again, recall this just equals to the derivative of the arc length, ds over dt. So just recall this right here. So ds over dt. All right, here I just teleported above again where we dealt with the fundamental theorem of calculus. Again, ds over dt equals to the derivative of the magnitude of the derivative of the vector function in terms of t, like that. And again, that's just from integrand. So this is the arc length function, and then derivative of this is going to be just this integrand inside, using the part 1 of the fundamental theorem of calculus. All right, anyways, so that's what we have. So again, I put that there just because when I upload this sections playlist, at least will be all complete if I upload this separately. Anyways, so this is going to equal to now r prime of t is equal to ds over dt. And then now we have multiplied by the vector, the unit tangent vector function, like that. And again, the reason we're writing this now, we're going to take the second derivative. So now we can apply the derivative. So the second derivative, and then we're going to use the product rule. This will equal 2. So then now the r double prime of t is equal to, and this one here is the first derivative of ds over dt. Yeah, now we're going to take the second one. We're using product rule, so we'll take the derivative of this first. This is going to equal 2, Yeah, it's going to be equals to d2, yeah, d squared over ds, yeah, ds, this is just the way you write it, and then dt squared. They put that like that just because at the bottom you're going to have a squared of the, I think the unit or whatnot, but anyways, that's the way you write the second derivative in this differential format. And then we just put this using, then we just add this one there, dt, t, capital T of t, a vector function, and then we use product rule. So then a product rule, we take derivative of this one times by this, and then add it to the derivative of this times by this. Now it's going to be ds over dt, and then now this is going to be derivative of this unit tangent vector like that. All right, now I'm just going to write in brackets product rule. It's product rule for vector functions, and I'll recap on this in a bit as well, as I always do. All right, now going further, so recall from an earlier video for the product rule. Yeah, I'll just recap it right now. So this is the product rule. Here's the thumbnail of it, and it shows you the proof. You expand it out. You do take derivative by components and eventually get this. Basically, if you have d over dt of a function f of t times by a vector function u of t, it's similar to this one here. This is just a normal function, and this one is a vector function. And then the derivative is going to be derivative of this one. Yeah, derivative of that one times by this, and then derivative of this, derivative of this one here times by the other one. So those are the derivatives, and you add them up, and so on. And this one's, if it's a constant, the derivative of the constant is 0, so that's just a special case of that. But anyways, you get this right here. And that's the proof there. Anyways, so I also recall from my earlier video showing that A cross A equals 0. So when you have a vector cross another vector, the same vector is equal to 0. And essentially what this means is if you have a parallel vector, so you have A, and if you have another one A, if it's all parallel, or B, even if it's B, that's equals to multiple times A, that doesn't matter. The cross product is going to equal to 0. So in other words, it's parallel. Yeah, so it's equals to, it's parallel. It equals to the 0 vector, and then yeah, so there's a link from an earlier video, and there's a screenshot from the calculus book. Yeah, because the thumbnail was actually it was more general. This was part of example 2. Show that A cross A equals 0, so plug that in into the cross product, add these all up, this all becomes 0, and so on. Yeah, and this, notice these all cancel up. Anyways, you get the 0 vector. All right, so, and also using the fact, yeah, so now we're going to use this. So using the fact that t cross t, the unit vector cross itself is equal to 0, we have, yeah, because we have so we have the first derivative, we have this, and we have the second derivative, and now we're going to cross those together for, because we're going to prove this right here. We're going to cross those and then show that the bottom is going to be the cubed length there. Anyways, so we're going to cross this and see what we get, and we're going to use this fact, the cross of together equals 0 of itself. So we're going to go r prime cross r double prime. This equals 2. Yeah, so this equals 2. Yeah, this equals 2. Well, let's write out the first one. So the first one is going to be this right here. So r prime of t is equal to ds over dt, and then this right here, the vector, this unit tangent vector. So ds over dt, yeah, over dt, and then this is going to be t vector function like that. I'll just put it like that. Yeah, I'll just leave out the small case t, just because it's going to be all over the place. But these are all functions of t. So we have that cross, and now the second derivative is this part right here. So that is that part. This is the second derivative, then this is t, first derivative, and then a derivative of the t there. So this is going to be ds, dts, whoops, squared t. Again, that's this one. We could just take the derivative, use it in our head. That's product rule. And then this is going to be plus ds over dt, and then this is going to be derivative like that. So we get that. All right, and using our cross product properties for vector functions, these are just properties for vector functions. We can actually just FOIL this out. So this cross product with this one plus this cross product with that one. So this equals 2, just for completeness. Calculus book just gives the answer, doesn't actually do this. So anyways, we'll do, and these are scalars, so we keep those outside. So what we're going to get is and I'll put a bracket for that, ds over dt, and then a d2, the derivative times by second derivative dt squared, and then this is going to be t, like that. Yeah, so we multiply that out, and then this is going to be crossed with this one. And that's the one that goes to 0. So we save a lot of room there. And then plus, so plus this one times that one, we're going to get a ds over dt squared. So these are the same one multiplied squared. And then we're going to have a t, t like that, capital T crossed with derivative of itself. Like that. So that's what we get. All right, so fascinating stuff there. Now this is one again, a equals to 0 using a equals to 0 vector. So this equals to 0 vector, and that's this part right here, 0 vector. All right, so now this whole thing equals 2, and yeah, this whole thing vanishes, so we're just going to be left with this right here. ds over dt, and then squared, and then multiplied by the, and those are scalars, we just take them out of the cross product vector function, and then the unit tangent vector, capital T, cross product with the derivative of the unit tangent vector, capital T, like that. So that's what we get. And this is equal to, yeah, this is going to be our, this is going to be, and also, yeah, this is not the length right now. We're just ignore the length right there. Yeah, this is just the normal vector functions there. I mean, the normal cross product. We'll do the length after. Like that. So that's this part. What we get is this part. All right, so now moving further. So now recall that the length of the unit tangent vector is just 1, because again, that's what's a unit 1, because you're dividing by the derivative, the length of the derivative r prime of t. So that's just equals to 1. Again, recall the definition. Yeah, going back here, recall that the unit tangent vector is equal to the derivative r prime of t divided by the magnitude of itself. Yeah, so basically the length of itself. So you're always going to get, you're dividing whatever this one is, the length, you're going to get just a unit length. This is going to be equal to 1. Because you're dividing by itself, the length. Anyways, going further. So, and then, yeah, so recall from my earlier video. So because this is equal to 1, in other words, equal to a constant for all t, so then basically, this means from my earlier video that t, yeah, so the unit tangent vector and its derivative are orthogonal by my earlier video. And recall the example 4 of my earlier video. Right here is a link to it that I showed. Basically, you have a sphere, is if you have any curve that's on a sphere like this, where the function is, the magnitude is constant, so it's always going to be constant. So if this case is 1, it's going to be 1, it's going to be a sphere of 1. It's going to be a sphere of 1, everywhere 1. And basically what it shows is that the derivative is going to be tangent to the sphere. In other words, it's going to be literally a giant sphere. So if this is constant, this is going to be perpendicular. And if it's perpendicular, dot product is going to equal 0. And yeah, so if it's perpendicular, it goes like that. And yes, it's the tangent vector on a sphere. That's how it visually can be seen. And this curve can be anywhere around there, as long as it's on the sphere. Yeah, so fascinating stuff. So again, you can see my video on that. So also recall from my earlier video on the length of the cross product. So the cross product length is equal to A cross B, and then this equals to A, the magnitude of A and B multiplied by each other. So A, magnitude of A multiplied by magnitude B, times by sine of the angle between them. All right, but in our case, these are going to be orthogonal, so the angle is going to be pi over 2 radians, or 90 degrees. Yeah, so in other words, this is going to be sine of 90 is going to be equal to 1, so it just equals to that. So thus, by the length of the cross product theorem, we have, again, this is from my earlier video, the links all there to it. Yeah, so that's what we have is the magnitude of the cross product of the r first derivative, r prime, cross with r double prime, is equal to, so the magnitude is going to equal to, using this formula. Well, actually, before we even get to that, let's just write down this part right here. So let's write what we have, because we're going to be using, we're using the unit tangent vectors, yeah. So let's just write it over there. This equals to ds over dt squared, and now we have this first, this is going to be unit tangent vector cross with unit tangent vector derivative, like that. And now these ones are the orthogonal ones. Yeah, so those are the orthogonal. Yeah, so then these ones are going to be orthogonal. And in other words, 90 degrees. So we're going to apply this one right here. All right, so this is going to equal to, again, this is going to be ds. It's just a scalar. So just keep that out of there. So we're going to take the length, and this is going to be the length. Yeah, I forgot to put this is the magnitude. This is a scalar and it's positive, just keep it out of there because we're squaring it. Like that. And now this is going to be now applying this one here. So magnitude of t and multiplied by magnitude of the derivative. So like this. And then magnitude of t derivative. And then this is going to be sine of theta, which is pi over 2. Yeah, and sine pi over 2, this is radians. This is again 90 degrees or orthogonal, like that. Just put it like that. So 90 degrees, like that. Let's put it one more time better. Again, I can't do it. All right, yeah, we got that. And now this one right here is just equals to 1. And again, just recall the sine function goes like this. If it's theta, it goes like this. This is how the sine function looks like. And this is sine theta, and this is at pi over 2. It goes to 1. So it starts off at 0, and then goes pi over 2, and it goes all the way, full cycles 2 pi. Anyways, that's how it looks like there. Let's put this like that. Anyways, and now this part right here, this is equal to, the length is just 1, because it's unit tangent vector. The derivative could be, doesn't have to be 1, so just leave it like that. So in other words, we get 1, now we get, this whole thing equals to ds over dt squared times by the length of this right here, d prime. I mean capital T prime, like that. All right, so we got that, and I'll move this over down here. So now this equals to, well, yeah, this is going to be the derivative of our the vector function, cross product with this, and then we take the whole magnitude of the second derivative, like that. And now what we'll do is I'm gonna solve for this one here. So I'm gonna take this over to the other side, like that. So basically divide this out. So what we're gonna be left off with is, and I'll write thus, the magnitude of the derivative of the unit tangent vector is equal to the cross product of the magnitude of the cross product of the first and second derivative of the vector function r, like that. Divide this by, and now we divide this whole by t ds over dt, the derivative of the arc length function in terms of t, divided by this one here. Squared, I mean. So divide by that and then squared, like that. And we already know what ds over dt is. We already, from just starting off with our proof right there, we showed that ds over dt, yeah, all the way back from the beginning of the proof, ds over dt is, well, again, it was just equal to the derivative of the vector function. So the magnitude of the derivative, so the length of that. So we already know that. We already started off with that, and that was from the part 1 of the fundamental theorem of calculus. That's just the integrand inside the integral of the vector function, of the arc length function as a function. So this equals to, this equals to right here, r prime, like that. That's just equal to r prime of t there, the magnitude there, like that. Yeah, so in other words, this whole thing equals to, and I'll move it down to make some more space here. So thus that this equals to, well, the top part is going to be the magnitude of the cross product of the first and second derivative of the vector function r. Divide this by, now this just becomes, well, the magnitude of the first derivative of the vector function r squared. So that's what that is. So that's what this one here, that's what this length of the derivative of the unit tangent vector is. And so that's what that is, and we know, well, kappa is equal to, again, recall what kappa is. That's just the curvature, and that is just, well, that's this one we're trying to prove right here. So we have the top part, the bottom part. This is just what kappa is. Yeah, so kappa is just equal to just equal to the magnitude of the unit a tangent vector derivative divided by the magnitude of the derivative of the vector function r. So we just put that in. So this equals to this magnitude of the unit tangent vector of t, like that, divided by, and again, we're just ignoring the t's, the small case t's, and this is divided by the magnitude of the vector function r, a derivative of r. So like that. So in other words, what we get is, well, this right here is just is this And now there's an extra term there. So we just put a cube there. So now that this whole thing equals to r, cross product derivative of this, of the first and second derivatives of the vector function, and then take the full magnitude or the length, and then divide it by, and now this becomes cubed now, of the length of the derivative of the vector function r, and then cube. So there it is, proof. And that's exactly what we were asked to prove in our theorem. That's right here. So there it is. That's kappa in terms of t. And then we just ignore the small case t's just for writing. Otherwise you'd be writing a whole bunch of small case t's. Anyway, so that's pretty fascinating stuff. All right, now let's go further and do an example on this and look at example for curvature of a twisted cubic. So we're asked, find the curvature of the twisted cubic. This was here again from my earlier video and one we covered a bit earlier. Of the twisted cubic, the vector function r of t equals 2 and has components t squared, and t cubed at a general point and at the origin at 0, 0, 0. Right, so solution. So we first compute the required ingredients, and what I'll do is actually, I'm just gonna circle this right here, just so we have this in mind, because we're gonna get the curvature, so we need to calculate this basically. Yeah, so we basically need to get this right here. So we gotta get this, these two, or these right there. All right, so what I'll do is, well, let's find the first derivative. So let's just write this down. So what we get is, so we first compute the required ingredients, and that's going to be, well, the first derivative. So let's just write down our twisted cubic vector function first. This equals to t squared, and t cubed in this triangle bracket format. So like that. So then the first derivative is going to be r prime of t. This equals 2. Well, derivative of that is going to be 1, 2t, and then the 3 goes down here, t squared, like that. And then the second derivative, is going to be, again, this is why it's typically easier or more convenient to calculate using this formula instead of dealing with this there. All right, so anyways, we got this, now the second derivative, this is going to be, well, 0, and this becomes 2, and then put the 2 down. For the other one, it's going to be 6t, like that. All right, so now the next setup is, well, we need to calculate, the next one, just do the bottom one right here. So the length of the first derivative, so that's going to be now, I'll just put another arrow. So this is going to be the magnitude or length of r prime of t. This equals 2, and again, this is going to be a giant square root, and then 1 squared, plus this is going to be, well, this one squared, so it's going to be 4t squared. Then the other one's going to be plus 9t 6 to the 6, like that. Actually, whoops, not to the 6. This is squared, so squared multiplied by 2. So that's going to be 4, not to the 6. All right, so what we'll do is, well, since this is part of this equation, and this one we're going to take the cross product, so we'll have the separate answer. So I'm going to circle this in. So that's the first part. That's this one right here. And then we just got to cube it. But then now the next part is this top part here. Yeah, so the top part, that's the magnitude of the cross product. So let's just write that. I'm going to write the full thing. We're going to go magnitude of the r of prime of t cross with r double prime of t, like this. Yeah, so this equals 2, and we're going to basically take the magnitude. I'll put a second one just because, just in case. So we're taking magnitude of the cross product, and this is going to be like that. So I'll put a second one just indicating its cross product, and it's going to be a recall. We need our I, J, K standard basis vectors on top for the cross product in indeterminate format. So we'll put this like that just for we're taking the magnitude of it. Afterwards. Well, first we'll take the cross product. So this again is 1, 2t, 3t squared. That's the first derivative. 1, 2t, 3t squared. And now the second derivative is 0 to 6t. 0 to 6t. And then recall how to take this here. So we're going to put this equals to, make some more room. This equals to like this. Take the we're going to take the length of their magnitude, so put that in the back on the outside this straight bracket, and now triangle bracket, and now put the terms. So recall, the easy way to do that, just cross this out, multiply these two, and then subtract by this multiple, like that. So what we're going to get is we're going to get a 2. That's going to be 12t times 6t is going to be 12t squared. And then minus, and now we're going to get a minus these two, so 2 times 3 times t squared, 6t squared, like that, and then subtracted by, now the next setup is these two in the middle, so we're going to cross 1 times 6, and then minus these two, like that. And so in other words, we're going to get a 1 times 6t, that's going to be just 6t. But it's a negative, because it's the middle one, that's the negative one there. So we're going to put a negative, that's going to be, well, 6t, and then, 6t, because remember the center is negative, the outsides are positive in their cross product. And now this one's going to be, yeah, minus 3t squared times 0, that's 0. Like that. Let's put it for completeness, put the whole thing out. And the next setup is the last one, is we cross out this one, multiplied by these two, subtract by those two. So we're going to get a 2 minus, well, 2t times 0, 0. And then close bracket, and then we take the length of that. All right, and also fix up this one there. So anyway, so we have that. So we'll erase our shorthand, shortcut stuff there. All right, and to simplify this further, so this is going to be the magnitude of this. 12t squared minus 6t squared is a 6t squared. And then this one's going to be just negative 6t. And then lastly, this one's just going to be 2, like that. And put this in for the magnitude. And now this equals to, well, this whole thing equals to square root. And now we take the inside. So this is going to be basically square of all the components and add them up. So 6 squared is 36. Yeah, so we're going to get, well, I'll put this, we don't even need to put that separate. So we'll put 36. And then t squared is t to the 4. And now this negative squared is positive. And then we're going to get another 36, and then t squared is t squared. And then plus, well, 2 squared is 4, like that. So that's what we get there. And we can simplify this further. We should have factored out the 2's out of there earlier. But anyways, this just becomes, well, factor out the 4. So this is going to be square root 4 times it by square root of 36. Yeah, that's going to be 9. 9 times 4 is 36. T4, like that. T to the 4. All right, and then plus 9t squared, and plus 1, like that. And then, in other words, square root 4 is just going to be plus or minus 2, but we'll only look at, consider the positive for the magnitude or length. So it's going to be 2, and then square root 9t to the 4 plus 9t squared plus 1. Yeah, so we could have just done this one instead, factor this out there. We could have been the 2 and put those all inside 3, 3, 1. But anyways, I just followed my calculus book. Next time I'll just ignore them and do it myself. All right. Anyways, what I'm gonna do is I'm gonna box this out, because that is this part right here, and that's the top part of the equation. So we have the top part, which is the magnitude of this cross product, and divided by this one here, and then that's this one here. But then we just gotta cube it. So thus, yeah. So what we get is, well, Thus, k as a function of t is equal to, well, the top part is just going to be 2 square root 9 to the 4, 9 power 4 plus 9t squared plus 1, all divided by, yeah, this one right here. But then we're going to have to power, instead of squared, it's going to be power of 3 over 2, because we have this cubed there. So cubed and then over 2. So that's going to equal to, put a bracket like that. That's going to be 1, yes, 1, 4t squared, 9t4. All right, whoops, my computer just fell down. But anyways, it's going to be 1 plus 4t, yeah, so 4t squared, 9t4, plus 9t to the 4, all to the power of 3 over 2. So that is our curvature. All right, yeah, so that's our curvature formula, and that's a general time t, so or general point. So this was, again, find a curvature of a twisted cubic at a general point and at the origin 0, 0, 0. In other words, because we have a t there, so at t equals to 0. So the second point, yeah, so at the origin, so then that's a general one, and at t is equal to 0, yeah, or again at t equals to 0, or or 0, 0, or just say or at 0, 0, 0. Yeah, so at that scenario, yeah, we could just plug in 0 for everything. So then what we get is, put a double colon there, so k of 0, I mean kappa of 0 is equal to 2, and then 0, 0, and then we have 1. 0 plus 0 plus 1 divided by, now this one's going to be 1, 1 plus, again, whenever you have a t, it becomes 0 plus 0, then 3 to the 2. Again, 3 to 2, power of, 1 to the power of anything is just going to be 1. So this just equals to this, the whole square root becomes 1, this just becomes 2. Like that. Yeah, so there it is. Alright, and now for completeness, I just wrote this down as well. So at the origin, the curvature is 2 for twisted cubic. Anyways, going further, so curvature of a plane curve that has an equation y equals f of x. So for the special case of a plane curve with equation y equals f of x, we choose x as a parameter and write, writing this in our parametric equation or vector format, but now it's in terms of x. So if we have r of vector function of x, and then just write this out in our standard basis vectors. I'm going to write x component, there's the xi vector plus, now I'll just put, for completeness, put the full thing y, this is going to be their j, but then y is a function of x, in other words, it equals f of x, so this equals to xi plus y is going to be, well, f of x, like that, j. Alright, so now the next setup is, well, we need to take the derivative, because again, we want to find the this setup here, the derivative right here, and then we'll take the cross product and so on, and then divided by the magnitude of the derivative, the first derivative cubed, and so on. So we need to take the magnitude of the cross product. So to get that, we need to get the derivatives. So this would be, or actually I'll write then, just because calculus book was writing then. So anyways, then we're going to get a r prime of x. This equals to, well, derivative of x is just 1, so that's going to be just I, plus, now derivative of this fx is just f prime of x, like that, j. Alright, so we have that, and so now the second derivative, that's again, calculus book just wrote and, so I'll just do that as well. So r double prime of x equals 2, and now the derivative of this one is constant, just becomes 0, so that just vanishes. So in other words, we're just left with this right here. So equals to f double prime of x. And this is going to be, j. Yeah, j standard basis vector, like that. All right, going further. So now since, because we're going to be taking the cross product. So since I cross with j, because these are perpendicular, this obtains the k. This is just this is just the I, this is the X or the I. Yeah, and then this is going to be the Y or the J, and then you get the cross product, it becomes all, these are all perpendicular. So you all get that, and this is going to be our Z or K vector. Anyways, I'll recap on this in a bit, but I just wanted to illustrate that right now if you're confused. All right, so this is going to be K, and also note that if you have the cross product with itself, again, as I stated before, is 0. So J cross J is equal to 0. Equals to 0 vector. So since that, then I can just take the cross product and then we can analyze that as we go. So we get r, the first derivative of r of x, r prime of x, cross with r double prime vector function of x. This equals 2. Alright, yeah, just fix that up, the bracket. This is going to equal 2. Well, let's plug these in. So the r prime is going to be that. So that's going to be I. So yeah, this is pretty interesting using these standard basis vector format like that. Plus the vector f prime of x, j. And then cross with, well, this one here is just, the second derivative is just f double prime. So f double prime of x. And this is going to be, I'll try to make the x look different from the cross product. Like, I'll make it bigger. So just because we have an x already, yeah, I'll make it bigger like that. Okay, one more try. All right, perfect. All right, and then yeah, this f double prime of x, this is j. So again, it's a vector with no x component, or the x component 0. All right, so what we end up having is, well, we could just take these, multiply these inside using just basic vector function properties for cross product. This is going to equal to I cross with f double prime. Actually, and this is a function. This is just a scalar, so we can move that out of there actually. So this just becomes, yeah, I'll just take this out, put it in the front, f of x, f double prime of x, put it out like that, and then put another bracket, but we're going to have I cross with j, like that, and that's the one that's equals to the k there. This equals to k vector. And now the next one's going to be, well, this is going to be multiplied or cross product inside, so let's just FOIL this out. And this is f prime, and these are scalars, so we're going to get is a f, I'll put another bracket, just get these out of there. And this will be, yeah, let's put a, actually we don't need to put a bracket there, put a bracket on the other one. So f prime of x multiplied by f double prime of x, and then times it by, and now we'll put the j cross j. So, and a cross product of a vector with itself is just 0 vector. Yeah, so this equals to 0 vector. All right, so in other words, this whole thing vanishes. So all we're left with is this, and this equals just the k there. So this equals to f double prime of x k, like that. Yeah, so that is, so that is the cross product. It's fascinating stuff. Actually, but instead of circling this, that's not what we actually want. We want the length of it. So I'll write, I'm just going to go, I'll say thus, the magnitude of r double prime, r prime of x cross product with the double prime of x, r function, like that. This equals to, well, this is just going to be square root of the term, all the components squared. So in other words, square root of f double prime of x, and then this is all going to be squared. But then we have a square root and squared, that just equals to f double prime of x. So that cancels out, and we're just left with itself. Like that, yeah. So that is the magnitude or the length of that cross product, and that's what we're going to use in our equation. And yeah, actually, I just moved things around, but actually to be more accurate, because this is, yeah, we're going to need the magnitude. This is squared, and then this whole thing square root, and the inside has to be positive. This is actually the absolute value of it. And this is not length because this is not a vector. So yeah, we also need to take the absolute value. So equals to this. Yeah, so that is that. Yeah, just make sure we have this, and I'll put a another box around. So it's the absolute value because we only want the positive values of it. Not the negative, because it could be negative and so on. So anyways, so that's what we have. And finally, we also have, so yeah, so we have this. Now the next component that we need for our equation, scroll back up for this. So we have the top. Now we just need the length of the this vector. Yeah, the first derivative vector function. So we just need that one. And so we also have, and we know this from earlier, from like way back in the beginning of the video. So we also have when we have just a y equals fx function, so we have this length right here of the first derivative. This equals to, yeah, we can go all the way back to the beginning of the video just to show you, or we can drive it ourselves. Anyways, I'm just going to scroll up. All right, yeah, so I'm back here. So yeah, again, remember the length, yeah, that's just going to be equals to that integral, but there's that inside term there. That was our r first derivative, r prime, yeah, of the vector function. Yeah, so that's going to be this 1 plus and then f prime of x squared. This is for if f, yeah, this is for the y equals fx curve there. And then of course I showed that yeah, all these are just the same thing as writing the magnitude of the first derivative of that vector function. Yeah, so that's what we have here. So that's the length. This square root part. Yeah, so that's what we have, but yeah, anyways, a teleporter back here. But we could also just take this again for completeness. Let's just derive it as well. So we have this right here, so the magnitude of this. Again, it's the same thing as I said way back in the earlier beginning of the video. This is going to be the magnitude of I, yeah, this is just to be I plus f prime of x. j. Again, the magnitude or the length, that just equals to now square root. And this is going to be this component squared. So 1 squared is 1 plus f1, f prime of x squared. Yeah, like that. That's it. Yeah, so we get that. I'll make this smaller. All right, yeah, so we have that. I'm going to box this because this is another part of our ingredients that we need. So that's why we put these together. So this is the top part, this is the bottom part. But then we need to cube it. Yeah, so again, scroll back up. And I keep scrolling because the terms are really big. Just to wrap it around my head. Anyway, so we have this top part, we have the bottom part, and then cubed. All right, so thus, put it all together. Thus, we have the curvature. I'll put it a bit lower. So the curvature is equal to, and I'll put this k better. Curvature of x is equal to, again, I think it's put it for completeness. This is going to be, yeah, here, yeah, actually, I think I just wrote it in my notes. I'll write, this is the original one we had. This is just for completeness. This is the unit tangent vector like that. Yeah, the derivative of the magnitude over this right here, just write it in both terms. Then r prime, magnitude of that, this equals 2, and then our second cross product format, just for completeness, x like that, cross r double prime of x over r prime of x cubed. So this equals 2. So now our case, we're taking this part right here, and that's going to be this f, the magnitude or the absolute value of the f double prime of x. So absolute value of that, so we get the positive value divided by, and now this is going to be this is squared, square root, but then power cube, that's going to be, this whole thing's going to be power of 3 over 2. So now we get 1 plus f prime of x squared, and then the whole thing is going to be, yeah, actually, calculus book, actually, instead of using the inside the square bracket, I'll use this as a just another bracket, and the big one we'll do squared over, yeah, that's power of 3 over 2. So there it is, that's our curvature. Yeah, so that is our curvature formula. I'll put this like this. This is curvature for the special case, the kappa, wait, this kappa better, like that. And this is a special case where we have a plane curve y equals fx. So epic stuff there. All right, and now we have that. And also now just a quick recap from my earlier video on standard basis vectors, just to illustrate again what they were, because we were using the fact that this I cross j, I cross product j equals to the k standard basis vector, and this one j cross j is equal to 0. So recall standard basis vectors, that's just along the x and y components. So we have the k is on the vertical one, this is the j, the j is on the y, and the x is on here. And these are, again, perpendicular. So if you cross this one with this, you're going to get this positive one, actually. There, it's pretty fascinating. And you can do the cross product yourself, and you'll find that, and so on. And then, so basically, when you have a vector from the origin, position vector up to this point, a1, a2, a3, its components, you could write them in the x, y, z, the triangle bracket, or just put them in the standard basis format, indicating it's all vectors. So you're adding up all the vectors together. So it equals to a1i plus this. So it goes from the bottom, and then if you add 3 dimensions, you need another one, a3, so it goes all the way up. So you add them. So it's just vector addition. And yeah, so j I cross j is equal to k. And if you have any of these crossed by itself, parallel equals 0. Anyways, pretty epic stuff. All right, and now let's continue further and now look at example 5. So curvature of a parabola. So we're asked to find the curvature of the parabola y equals x squared. So again, this is y is just a function of x at the points 0, 0, 1, 1, and 2, 4. Well, again, we have our equation for curvature right here, which equals to the absolute value of the second derivative of f of x, f double prime of x like that, and then divided by this right here. So what I'll do is I'll just copy this just to make things easier. Whoops, I'll scroll back up here. I'll copy this and then I'll paste it there, just so we save some time. All right, copy and paste it right here. So this is our curvature. And now we just need the second derivative and so on. So Yeah, so what we have is, let's just write this down. So we have y equals x squared, and again, this is just a function of x, like that. This is our f of x. Yeah, let's write that again. So f of x like that, and then the derivative we get, well, y prime is equal to, bring the 2 down to, and then subtract a power, so 2x, and again this is equal to just f prime of x. Just for completeness, and then lastly, to take the second derivative, we get, well, 2. That's our f double prime of x. Again, same thing. Just throw that in there, and then what we end up having is, put it like that. This is our kappa of x is equal to, well, 2 divided by, so the absolute value of f double prime of x is just 2. There, and then divided by 1 plus, and then f prime of x, that's this part right here, and then squared. So that's going to be like this. I'll put a 1 plus, or I'll put a regular like this. Actually, yeah, I'll just put it like this. Yeah, I'll just save time. Instead of, this is 2x, replace that over there. So plus 4x squared, 2 squared. Yeah, so yeah, 2 squared and x squared, like that, and then all of that to the power of 3 over 2. So this is our answer. So that is the curvature of the parabola. Yeah, so y equals x squared. The curvature of it is just this. All right, yeah, so that's our curvature, and now the next setup is, well, we need to find the curvature at these points 0, 0, at the origin, at 1, 1, at 2, 4. So the curvature at 0, 0 is just at, at x equals to 0. Yeah, so we'll just put that in. That's going to equal to 2, and you can just see that right here. So we'll have kappa of 0 is equal to 2 over, well, 1 plus 0, and then power of 3 over 2. And then power of 3 over 2, 1, power of 3 over 2 is just 1, so it just equals to 2. So there it is. That's just like that. And now the next setup is, yeah, so the next setup is at 1, 1. So we're asked at 1, 1. The next one is 2, 4. So at 1, 1, the curvature is, you'll have kappa of 1 equals to 2 divided by 5, because if we put a 1 here, it'll just be a 1, and then be 1 plus 4. And then that'll just be 5. Yeah, so equals to 2 over 5 to the power of 3 over 2. And then again, for the calculator in my OneNote, you got to write it like this. And then you could just use the built-in calculator. And this equals to equals space. Yeah, so 0.1789 or approximately 0.18. And also, again, just to write this for completeness, if you write kappa of 1, this equals to 2 over 1 plus 4 times 1. So 4 times 1 is just 1. Yeah, so 4 times 1 is just 4, and then 3 over 2. So it equals to 2, 5, 3 over 2. So that's exactly this right here. All right, so that's what that is. I'll just box this in. And then the last one is at 2, 4. All right, so at 2, 4, well, x is 2, so then we'll just plug in, and this is a function of x, so we just plug in 2 in there. So k of 2 is equal to 2 to the power of 17. That's because 4 times x squared, so 2 squared is 4 times 4 is 16, and then plus that 17. So in other words, I'll just write this, and then we'll solve it, or calculate it. So this is going to be the kappa of 2. This equals to 2 over 1 plus, this is 4 times, well, x squared is 4. Yeah, so that's 16. 16, and then add them all up. This is 3, power of 3 over 2. This equals to 2, 17 to power of 3 over 2, like that. And then if you just write it like this, 2 divided by 17 to power of to power of 3 over 2, and just write it like this with the proper brackets, you can calculate it with the built-in OneNote calculator. For example, equals space, like that, and then this is 0.0285 or approximate 0.03. It's fascinating stuff. All right, going further. So observe from the expression for kappa of x, or the curvature as a function of x, or the graph of kappa in the figure below, and I'll draw that soon, that kappa of x approaches 0 as x approaches plus or minus infinity. You can also see this from here as well. As you go to plus or minus infinity, the bottom is going to be, well, 4 infinity squared, and then all to the power of 3 over 2. This just gets infinitely large. So in other words, if you're dividing by infinity, 2 divided by infinity, you're going to approach 0. Doesn't matter plus or negative. So you're going to have it, so plus or minus. So it's approaching 0 as x approaches plus or minus infinity. This corresponds to the fact that the parabola appears to become flatter as x approaches plus or minus infinity. In other words, it becomes straight and less, there's basically less curvature. And you can see this, I'll graph this all out right here. So let's see, and then I'll probably use the screenshot from Kaka's book. All right, so let's say we have here, this is our x. And then this right here is our y. There's the origin. And then we have a parabola. Oops, we have a parabola like this. And then at the at y equals x squared, so at x equals 0, y is 0. It goes like this, but then becomes almost flat, almost straight. Like that. And this is y equals x squared like that. Yeah, so that's y equals x squared. And then now if we draw the other graph, I'll do this in red. So this one will do this in red. Yeah, this one is now, remember here it's at 0 at the origin, it's 2. So for the curvature, it's going to go at 2. It's going to be 1, 2. So this is at point 2, and then it goes as you go to infinity, it just smooths out. It goes like that. Whoops, I'll make it like this. Yeah, it goes something like that, but it's actually a bit more smooth. I'll just draw it like this. All right, and then this one just goes like that. And this is our, this is at 2, and this is our kappa of x, like that. Yeah, also further, just to understand how the curve would look like, well, at 1, at x equals 1, we get this 0.18, so it actually goes much smaller. So this would be 1 roughly, actually, yeah. So if this is 1, so we'll just, if this from here to here, if it's 1, yeah, it should be somewhere around here. So this is 1, and then this would be about 0.18 over there. So again, it's not the x and y are not to scale, and this is going to be roughly here, negative 1 like that. So yeah, that's how it is. And I think I'll just use the, I'm going to erase this and just use a screenshot of the calculus book, because again, graphing manually is much harder than just using the actual graph like this. All right, so this is one from the calculus book. Again, yeah, it is much sharper up like that and goes down, goes back down like that. So fascinating stuff there. Yeah, so the parabola y equals x squared and its curvature function. So there it is, epic stuff. And again, note at 1 at x equals to 1 here. This is if you draw a cube from this one here. Yeah, so this is about 0.18. Yeah, so that's 0.18 right there. Epic stuff there. All right, furthermore, I've graphed this in Desmos 2D graphing calculator, so instead of using the GeoGebra, but this one, Desmos has good 2D, doesn't have a good 3D, and so on. So if you just plug in y equals x squared and then plug in the curvature formula, 2 over 1 plus 4x squared power of 3 over 2, you get this curve like that. It's fascinating stuff. And then we'll go to the curve, and there it is. You can play around with it, and so on. Make it bigger like that. Yeah, so you can play around with that. And I'll see the point here at 1 and 0.18. Yeah, so right there. Fascinating stuff. Yeah, so epic stuff. All right, now let's continue further and look at the next section. That's the normal and binormal vectors. So at a given point on a smooth space curve, so yeah, there's no sharp edges and so on, there are many vectors that are orthogonal to the unit tangent vector right here. This is the, again, remember this one, that's capital T vector. That's just r vector prime over absolute value of r vector prime. So it's equal to magnitude 1. And just point in the direction of the tangent. Yeah, it's in the direction of the curve. So we single out 1 by observing that because this right here, the length or the magnitude of this unit tangent vector, capital T vector, equals to 1 for all t. We have, now if you take the dot product, because it equals to 1, because it equals to 1, so it's a constant, so then the derivative of it is going to be orthogonal. So then basically the dot product will be equal to 0. And again, this is from my earlier video. I already discussed it earlier. If you go back to that giant 3D graph right here. Yeah, so if this function is constant, then its derivative is going to be orthogonal. In other words, the dot product will be equal to 0. So basically, if it's constant, the distance is constant, it's the equivalent of being, the surface is going to be on a sphere. Doesn't matter what the surface space curve looks like, it's going to be on a sphere because this distance is constant away from that. And then the derivative is always going to be tangent to it. And tangent to the sphere or orthogonal to this pointing vector. This right here. Yeah, so epic stuff there. And then the dot product is going to be equal to 0. So let's go back. All right, yeah, so we single out 1 by observing that because this unit tangent vector, the distance equals to 1, for all t, we have the dot product between the unit tangent vector and its derivative equals 0, and this is, equals, and it's a scalar. Remember, dot product gives you a scalar by my earlier video shown earlier. So, so again, so the derivative of the unit tangent vector is orthogonal to the capital T, or the unit tangent vector. So note that t prime itself is not a unit vector, so it doesn't have to be equal to 1. It could be equals to other stuff like that because it's the rate change of this unit tangent vector. So, but at any point where, the curvature is not equal to 0, we can define the principal unit normal vector as capital N of t vector function, or simply unit normal as, we're going to define this as, because this is not a this is not a unit vector by itself, what we'll do instead is we'll just get a unit vector out of that. So using this unit normal, because again it's orthogonal to the unit tangent vector, so we're going to take this vector, this derivative, which is orthogonal to the tangent vector, and then divide it by, well, the length of it. Just take the unit vector, so divide by its actual length, so that we're going to get always 1. So whenever we take that, it's always going to be 1. All right, so now that we have this, basically we have this unit normal, so normal vector tangent to the unit tangent vector, so that's orthogonal to 90 degrees. And now if we take the cross product of these two, so cross product, so the vector, and we'll call that capital B, like that, and it's basically the cross product, and cross product is always going to be 90 degrees from these two terms there. So the cross product of the unit tangent vector with the unit normal, or the principal unit normal vector, I'll just call it unit normal, is called the binormal vector. So remember, this one is orthogonal to t. So so this n is orthogonal to t, and this one is orthogonal to both of them. So they're all just orthogonal. And this one's called the binormal vector. So this one is binormal vector. It is perpendicular to both the unit tangent vector and the unit normal vector, and is also unit vector. See figure below. And the reason it's a unit vector is well, because these are both unit vectors, and then cross product with it, you're just going to get a 90 degree unit vector, similar to the standard basis vectors setup I showed earlier. But anyways, so what we'll do is now, so how this will look like is this. So if you have a curve like this, like that, then it goes underneath, and I'll draw it. I'll use the screenshot again, just because I'm getting used to that. I haven't done that before, but I started doing that now. So now if we take a point like that, and then what I'll do now is, so now I'll just change it into red. So let's say we have a point here, and this is so that's the curve C. So now we're gonna get a tangent vector like this. This is the t, capital T, like that. That's tangent vector. And then the 90 degrees to this one is going to be the, and the normal one's always pointing actually inwards there. It's going to look something like this. This is going to be pointing away from this. And these are all unit vectors. So I'll put this all, all of these are unit vectors. It's going to be n, like that. And this is 90 degrees from that. And now the next one is going to be, well, 90 degrees to both of these. It's actually be pointing like this away, and it's all going to be, all of these are the same length of 1. This is going to be binormal of t, and it's going to be something like this. All right, so that's going to how it look like. Yeah, that's how it look like. So you have all of these, and they're all right angles to each other. So quite amazing. All right, and here I quickly pause the video and just deleted my drawing. Just use the screenshot of the calculus book. It's a pretty good graphic right there. So so we have this curve, and then we have the normal unit tangent. This is the normal one. This is the binormal. Is the tangent vector, and they're all of these are gonna be unit vector. But actually, I just noticed something on this this one right here, these arrows, if these are all unit vectors, they all have to be the exact same magnitude. So this is wrong. All right, so I'm gonna first time I have to say no. I'll have to go back and use my actual drawing. So I think my drawing is, even though it doesn't look as nice, it's still better than this one, because that's wrong. It needs to be shorter. So I'll just go back. I'll undo. 1 second. Oh, all right. Here I quickly paused the video and then I used my drawing instead. And I made this a bit shorter so that these are all length 1. So again, the important thing is the lengths of these ones are 1. Length is 1. So the length is 1. Length is 1. But again, these are all unit normal vectors. So length is 1. So again, that's why Calculus book was wrong. This is correct. Anyways, I put those there. So you can think of the normal vector right here as indicating the direction in which the curve is turning at each point. Yeah, so that's an interesting thing. The normal one is always on the inside curve. So that's quite fascinating stuff there. Yeah, so I'm not 100% sure why, but it's probably just the positive direction is the inwards curve. So yeah, that's something to think about. Anyways, we'll see if that arises in example 6. So anyways, going further, so example 6, unit normal and binormal vectors of a circular helix. So we're asked find the unit normal and binormal vectors for the circular helix, and this is the vector function r of t equals to cosine t times I vector, I basis vector plus sine of t times j j standard basis vector plus t plus t k vector. So solution would be first compute the ingredients needed for the unit normal vector. Yeah, okay, so before we get to the ingredients, well, let's just write down our normal vector. So we're going to get the unit normal first. We'll do the binormal after. So the unit normal is this one. The binormal is the cross product one. All right, so let's write this down first. So the unit normal is going to be n of t. This equals to the derivative, like this, of the unit tangent vector over its length. Over the magnitude or its length, like that. Tangent, with a prime there, and also we know that the unit tangent vector, that's just this one right here, is equal to, again, its vector like this. This is going to be this equals to, actually no, this is the other one. This is just a tangent of the vector function divided by its length. Again, just remember that one. All right, and then this is the tangent like that. The length of divided by its length. All right, so now the next setup is well, we have this. Well, we got to get this unit normal one. So to get that, we need this this right here, the derivative of this part here. So we need to take the derivative of the unit tangent vector, and the unit tangent vector requires the second derivative of this vector function. So the first thing we do is take the derivative of this vector function. So we're going to get the derivative r prime of t is equal to, well, it's going to be derivative of cosine is just negative sine t, and we do it component by component, plus now derivative of cosine is just of sine is just cosine t with just positive, and then plus derivative of t is just 1. So that's going to be k vector like that. So we have that top part. And now the length of it, I think we already saw this before. It should be, again, pretty straightforward. So this is going to be now the length or the magnitude of the second derivative of the vector function. This equals to the square root. And then square each component, but this is a sine, negative becomes positive. Yeah, we get our usual Pythagorean identity. So sine t squared plus cosine squared t, and then plus 1 squared is just 1. So what we end up having is, let's put a 1 here for completeness. Now this, I'm going to square that for completeness. This equals to 1, that's Pythagorean identity. So we get a 1 plus 1. In other words, we get a square root 2, like that. Yeah, so again, we did this, I'm pretty sure, at least a few times. All right, so we have that. All right, so we have that. So the next setup is, well, the unit tangent vector, like this. Just do it like this. Unit tangent vector is going to equal to the second derivative vector, and then divided by the magnitude right there. So this equals to, let's put this at the bottom, 1 over square root 2, and then times it by, now this, just plug this in. So negative sine t I plus cosine t j plus k. All right, so we have this and that. All right, now the next setup is, well, we have this. Now we take a derivative and define its length. So the derivative is going to be, the derivative like this of this unit tangent vector is going to equal to, well, again, this is just a constant to keep that out. So derivative of sine t is just going to be negative, nothing changes, so a negative cosine t just becomes, the negative stays. Cosine t I, and then this one's going to be, well, cosine t derivative is negative sine t j, like that, plus, and then derivative of this constant is just 0. So we just leave it out. So we don't even need to write it like that. Yeah, because that just goes to 0. So now the next setup is, we'll take the length of it, or the magnitude. So we get the magnitude, or the length of this second, or of this first derivative of the unit tangent vector is equal to, well, now we're gonna have to take the take the magnitude. Well, it's gonna be the square root, but this is a scalar, so we just take that out. And what you actually, I'll just keep the negative in there, but we'll just take this one out like that. So what we'll end up having is, we'll just put this, because you can put these inside and you'll have to take it out anyways. But what I'm gonna do is I'm gonna just take this out, 1 over square root 2, and then we're gonna have a square, because that's just gonna be, again, that's just a constant. Yeah, because we could put this inside each component, and then we could square it. Then when we take it out, we have to square it anyway, so nothing changes. So anyways, so now this inside, the negative becomes positive. So then we'll just do the same thing, and then it's gonna be just, again, cosine squared t plus, and then this is gonna be sine squared t. Again, the negatives just disappear because we're squaring it, becomes positive. And again, it's always a Pythagorean identity when we're dealing with circular, circles, or circular helix and so on. Anything with circles, we're going to get this a lot. And also, this is just for this chapter, just to illustrate it so that it's easier to calculate. Anyways, that goes like that. And then this becomes, well, 1 over square root 2. So that is the length of the first derivative of the unit tangent vector. So now we have all our components for all of our ingredients for the unit normal vector. So plug that inside and we'll get the answer. So the unit tangent vector is, so the unit tangent vector, like this, vector, unit tangent vector function equals to, let's put this for completeness, the derivative of the unit, this is the unit normal vector, is equal to the derivative of the unit tangent vector divided by the length of the derivative of the unit tangent vector. Like that. And then this all equals 2. And this equals to, the top part is just this one right here. Actually, not that top part, it's this one here. So this one right here. And then we're going to divide that. So what we're going to get is a 1 over square root 2 divided by a 1 over square root 2. That's the bottom one. This is 1 over square root 2. And then multiplied by this whole thing. So these ones will just cancel. And this is going to be this whole thing. Negative cosine ti minus sine t j. And the k term is 0. And those just cancel. So this equals 2. This equals 2. I'll just write this as negative cosine ti and minus sine tj, and in the other triangle bracket setup, this equals to negative cosine t, negative sine t, and 0. So there it is. I'll box this one out. It doesn't matter which one I use, but I'll box that out. All right, and I'm boxing this one out again because we started off in 3D and then we just got rid of that K term, so that this one, just to make note that again we're dealing with 3D, not a 2D plane like this IJ, but we're actually this would be, if we were just graphing out this function itself, we'll get a 2D plane on a 3D surface. So again, the key point is we start off 3D. Anyways, so this shows that the normal vector at any point on the helix is horizontal and points towards the z-axis. All right, and to see why this is the case, actually it took me a while. So if you look, this is the unit normal vector. If we just take a look at the function itself right here, so r of t equals to cosine ti plus sine t j plus tk. So we could see that, well, we know this is equal to, well, the same thing here, cosine and then sine. Yeah, so we have cosine and then sine, but then we have no k component. So I'll write this in triangle bracket. This just equals to cosine t, and then this is sine t, like that, and then t, like that. But then this one has it's the exact same thing, but but there's no sine there. And then where normal is just equal to, I'll put it next to it. This is going to be, I'll just put the negative out. So negative cosine t. And then yeah, sine t, and then 0. So the 0 is horizontal because there's no z component. So if we were to graph this out, just in a quick fashion here, calculus book doesn't explain why I'm doing it myself. So if this is the origin, this is the z, like that. It's the origin. So let's say we had a point here, and it's going to be, let's say it's a distance on the x-axis. This distance is going to be cosine t, and then the y component is here. Yeah, that's the y component. I'm only looking at a horizontal plane at the origin or at the bottom there. Yeah, this right here is sine t, and then the position vector is going to be pointing towards this. But then now we're going to have the minus of that. So in other words, the position vector we're dealing with is going to be, well, from here. Yeah, this right here is going to be our, I'll put, like this is r of t. And then the reverse of that, if it's just a negative, is going to be pointing the other way. And if you were to graph from the actual point here, so because it's the exact same thing but negative, and it's horizontal, this is going to be, yeah, it's pointing towards the z-axis, like that. That's unit normal. So yeah, it's pretty epic stuff. All right, so now let's go further. Now let's look at the binormal vector, because we were asked to find the unit normal and now also the binormal vector, and they're both unit vectors. So the binormal vector, that's just this part right here. We'll take the derivative of the unit tangent with the normal vector. And again, the unit tangent was this term right here. So what I'll do is I'll just copy this. Yeah, I'll copy that. So we're going to do that all right here. So this is going to be the unit. Actually, we don't even need to copy that. I'll just leave that out. So the unit, yes, so the binormal vector is equal to the unit tangent vector of t cross with the unit normal vector of t. And then, since we're dealing with the unit, since we're dealing with cross product, I'll write it in indeterminate format. It's easier to handle, but I'll take out the scalar. So again, we don't need to copy and paste that actually. So we just take this, put this 1 over square root 2 out of there. And then the unit normal was just this. It doesn't have a scalar. Besides the negative, you could include that. Yeah, actually, I'm not going to include that negative. I'm just going to keep it there, just because we might have to think, might have to like take out some of these as well. But anyways, what I'll do next is I'm just going to put this out of there. So that's just a 1 over square root 2. Well, actually, you know what? I will take it out. I think calculus book doesn't do it, but I think I'm going to get the same answer. If I don't, I'll just pause and redo it again, and you'll never hear from me. I'm going to take this negative out as well, because I just don't want to deal with that. We'll leave it out of there. And because again, we're going to be taking the absolute value, so it doesn't really matter, or the absolute value when you take the length and so on. No, actually, never mind. We're not actually taking the length, but so this shouldn't change the value. Anyways, we'll take the negative out, so it's going to be our I. This is going to be our J. It's going to be our K component, and then this one's going to be this is going to be right here. Where is it? Yeah, this is going to be negative sine t, cosine t, and then 1. Actually, this should be t there. Yeah. There's no t. Yeah, because that was a derivative already. So this is going to be negative sine, cosine, and 1. Negative sine, cosine t, and then 1. And then this one here, because we took the negative out of this normal vector, was going to be cosine sine. Just make it easier on us. Cosine t, sine t, and then the next one's 0. So we do that. Now this is going to be, this equals 2, again using the method, we cross out those, multiply these two, subtract by these two. So that's going to be, and this is going to be, I'll put this 1 over square root 2, and then bracket, this is going to be cosine t 0 minus, so we're going to have a minus right there, sine t times 1. So that's going to be sine t. So that's, we have a minus as well already there. We're going to have to multiply the negative side just to get rid of that. But anyways, you get the idea. So now the next setup is we'll remove this. Yeah, let's remove that other one. I'll now cross the center, and now the center has the negative. Here, just cross that out there. Yeah, sometimes my pen stops, just freezes because I think it's an old tablet I have, and it's an old Surface Pro 3, and this notes document is getting pretty big. So anyways, now the next one's gonna be sine t multiplied by this 0. So that's gonna be 0, and then but then we're doing a negative here, so 0 minus, and then this is gonna be 1 times cosine t. That's just gonna be cosine t like that. And then the next one's going to be erase this, cross out this one, and now we're going to do this minus this one. But only the middle has a negative there. This is going to be negative sine t, so that's going to be negative sine square t minus, and now that's going to be cosine squared t. Like that, yeah. So that's what we get. And this one here is going to be negative, again, negative, this will be positive. So in other words, this equals to the Pythagorean identity, but the negative side, so this will be negative 1. So that's negative 1. And then we'll just put the negative inside. So yeah, I shouldn't have taken the negative out. But anyways, just fun exercise. So this is going to be 1 over square root 2. I'll put the negative back inside. It's going to be sine t. Like that. And then this is going to be negative. This one's negative, it's going to be positive, but they put the negative back in. So this is going to be negative cosine t. And then this is going to be negative 1, but then we have this negative there, just put a 1 like that. So that's what we get right here. All right, yeah, so we get 1 over square root 2 times sine t, and then the components are sine t, negative cos t, and 1. And that's the binormal vector. So pretty fascinating stuff there. All right, going further. So the figure below illustrates example 6 by showing the vectors t, n, and b at 2 locations on the helix. And basically, this is, yeah, I'll definitely use the screenshot in a bit. I'm just going to graph this out. So if this is their z, this is what Calculus book does. This would be our x. They made it like this, so you get it from this view. Is our y. And so that's our y. And then let's say we had a graph like this. And then it has the points, and I'll draw this in red now. Yeah, so it draws it in red. It has 2 points. So if you have a tangent like this is t. That's our t tangent. The one's always pointing towards the z-axis. It's going to be like this. This is our normal vector. And then the bi one is going to be somewhere like this. It's going to be up, up, down like that. This would be the binormal. And then another point is just put it over here. This is closer over there, t. And then the normal one is going to be also pointing to this one, normal. And then the b vector is going to be sticking out like this somewhere. And it's always, again, a cross product, so it's going to be right angles to that, and so on. So it's going to be something like that. And yeah, here I should quickly pause, remove my drawing as added the screenshot from Calculus book. So if you have this curve like that, and you can see how the tangent one's changing, the normal's changing, but the normal's always pointing to the z. It's interesting. And then you have this b1 is just moving around and so on in 3D as this is changing. So, and also further, here's a graph of the helix along with its unit tangent, unit normal, and binormal vectors in GeoGebra. I'll put this in GeoGebra. So again, this GeoGebra is quite an amazing graphing calculator. So here it is. You could just write curve cosine t, sine t, and then this is like that. I set there and then set the variable a. So what you could do is write t as a vector. And the way to do this, if you notice what I did, was I would basically, you have this part here using a, because I can alter it. And this is the helix and t. Gotta be careful of the variables. I used a for this one, I think, because I don't think you can use t. But anyways, so this is the way. This is the starting point. And then the second point is the same one plus this is the t1 plus the tangent vector. So you have to go to that starting one on the helix. That's why I have cosine, sine, and t, but this is a. Yeah, cosine, sine, and a. That's just t. And then added to this one here is 1 over square root 2. That's negative sine, cosine, and then 1. That's the unit tangent vector right here. That's this part right here. So I have to add it because if you just graph it by itself as just position vector from the origin, they'll just be like, this would just be, this is the t, that'll just be the origin. So you have to actually add the vectors, the position vector plus all of these ones. Yeah, so that's what I did. And then the next one, position vector here. Well, we get to the point and then we add to the normal vector, negative cosine, and then negative sine and 0. And then the binormal, we get this right here, add this 1 over square root 2 sine negative cosine n 1. Like that, fascinating stuff. All right, anyways, what we end up getting is this curve like this, and it play around with it. So you click the link, and we get this graph, and it's quite amazing. And then you can move it around. The cool thing is you can literally, I had this pi over 2. I'll just put a. I thought it should be just a variable. A like that, yeah, so you can now alter it. I had this at pi over 2 yet, but anyways, you could see how it's changing. Notice n is always pointing. Yeah, so notice n is always pointing towards the z-axis, which is quite amazing. So n is always pointing there. Tangent's always pointing tangent, and then notice the b. The b's turning. So the b's one's turning along with it as well. It's pretty amazing. And it keeps going on and on. So again, notice that n is always pointing to the z. Yeah, to that. And also remember, it's actually equal to the position vector, but in reverse. That's why it's actually right on it. So that's pretty cool. Yeah, so that's pretty actually amazing. I'll close this. Yeah, so that's pretty amazing. And actually, some more stuff I'm going to show you there. Yeah, so for more stuff before we get to that. So notice how this was pointing, but it's also equal to it. This one is literally equal to it because it's the exact same setup here horizontally. Negative, but it's just a negative sign of it pointing inwards. All right, so now if we go back to this one, this is for the later plane. So if we have this, and if you go up from the top, you can see the circle. Oh, it's actually this one. It should be a circle like that. Yeah, just move the axis. Yeah, so notice that it's pretty amazing, absolutely amazing. So you can see that corkscrew there, helix, but from the top it's a circle. It's a circular helix there. So yes, amazing stuff there. Leave that. All right, so going further, so this all brings us to, so these tangent vectors moving across the curve there. This brings us to the T and B frame, in other words, the tangent, normal, and binormal frame, and also I'll also go over the normal and osculating plane. So in general, the vectors T, N, and B, starting at the various points in a curve, form a set of orthogonal vectors called the T and B frame that moves along the curve as T varies. So here's a screenshot from our just earlier that I covered as well. So that this one here, make it earlier. Yeah, so as T varies, you're gonna have these all just moving along with it, as shown in that GeoGebra clip right here. So if you have this set up like this, and you just change the T, in this case is RA, just goes up and up. Yeah, so the T and B frame just follows along that curve there. So fascinating stuff. All right, so this T and B frame plays an important role in the branch of mathematics known as differential geometry and in its applications to the motion of spacecraft. The plane determined by the normal and binormal vectors n and b, so n and b there, like that. So in this case, it would be like this. Yeah, so n and b at a point on a curve is called the normal plane of C at P, so that's the normal one. And then it consists of all lines that are orthogonal to the tangent vector T. So in other words, these are all the points, and again, it will expand out to all points. But basically, that's the plane, and that's going to be orthogonal to T. Yeah, so orthogonal to T, to the tangent vector T. The plane determined by the vectors T and N is called the osculating plane of C at P, and the name comes from Latin osculum, meaning kiss. So the T and B, I think that's what I was saying. Yeah, the T, T and N. So T and N. So N and B is the normal plane, and then the osculating one is T and N, so that's this part right here. But it again extends out further out, and it's kissing the surface. I mean that space curve. And then in this case here is going to be this one here. It's just kissing it there. But again, it expands out to all space, like that. All right, yeah. So the osculating plane. So it is the plane that comes closest to containing the part of the curve near P. For a plane curve, the osculating plane is simply the plane that contains the curve. Yeah, in other words, the plane curve, that's a 2D one. So in other words, if it's 2D like this, it's just basically the entire plane that contains it. So the entire thing is the osculating one. So yes, quite fascinating there. All right, and going further, we can basically illustrate all of this. And yes, illustrated with example 7. So normal and osculating plane of the circular helix from our example 6. So find the equations of the normal and normal plane and osculating plane of the helix in example 6 at the point P has coordinates 0, 1, and pi over 2. And again, from example 6, we have this helix right here, circular helix R of t. Is equal to cosine t I and plus sine t j plus t k, and those are the standard basis vectors. That's a vector function. All right, so let's take a look at the solution. So the normal plane at P has normal vector, and this is going to be the derivative of this at pi over 2, and this equals to negative 1, 0, and 1 since, and again, the calculus book just writes this. It doesn't explain why, but anyways, I'll do the rest of it. And basically, if we have the curve, let's say the curve is like this. It goes over here, and here's the point P. So this is point P. There's our curve C, like this. So the normal plane is going to be, well, we're going to have the normal vector n, like that. We're going to have a tangent vector t, like that. And this unit vector, so again, I just draw this for clarity's sake. It's the same length as this normal vector. So roughly the same length. Yeah, here I just fixed those up. This is going to be our t. Normal, that's our tangent vector, like that. And this equals to, and also this is normal to this one, so it's normal. So the plane is going to be like this. I'll just draw a plane like this. Normal to it. Yeah, so I'll just draw a plane. Also, instead of getting it in the way there, I'll just draw it like this, something like this. Like that. Yeah, so anyways, it goes across there, and I'll make this so that's behind it. Whoops. Yeah, so anyways, like that. So this is perpendicular to it, and this equals to, remember this one, the tangent, unit tangent vector is equal to the tangent, the derivative. So the derivative of the vector function divided by the length of it. So we get the unit vector there divided by the length of that derivative. So in other words, if this is normal as well. So this is normal as well. This is just going to be, this divided by just makes it, think of it as multiplying by a scalar, which it actually is, and then basically you're just going to shrink it to length 1, but it's going to be also perpendicular. So normal, I'll just put this like this. Normal is perpendicular, so normal plane has a normal vector. Normal to normal, I'll make this normal. Normal to normal plane. All right, so that's what we have. So at P, which has 0.10 pi over 2, this is, well, this point right here, because the vector function is, the z component is just t, so cosine t, I, sine t, and then this is t, that's just, that's the z component. So at pi over 2, that means t is pi over 2. So at this one, this is t equals to t. So then, again, this is because, so pi over 2 is t, and again, we have r of t, the vector function. This equals to cosine t I plus sine t j plus t k, like that. Yeah, so thus the derivative, so thus take the derivative of the vector function, thus to get their normal vector. And then once we get the normal vector, we could use the equation of a plane to solve it. So this can be derivative t, and we already solved this before, but anyways, cosine t is going to be negative sine t I plus, and then cosine, the derivative of sine is just cosine. Derivative of cosine is just negative sine. All right, and then j, and then t derivative is just 1, so we'll just put the k like that. So that's what we have, and now we could plug in our t equals pi over 2. So now the actual value, so the actual vector at t equals pi over 2 is equal to, well, we're going to get now negative sine pi over 2i plus cosine pi over 2j plus k, like that. So which is just 1. And now just to recall our graph of so now this right here, this right here, the sine pi over 2, that's actually just if you plug that in, that just equals to 1. And I'll show you, I'll illustrate it in a bit. But this equals to just 1, so put the negative, so negative I, or I'll put it like this. But if you put in the square bracket, I mean the triangle bracket, this equals to -1. And then cosine pi over 2, that's just 0. And then the next one is 1. So this is and this is exactly what the calculus book wrote, -1, 0, and 1. So that's the vector. So we have this. So that is our normal vector. And again, just recall Pythagoras, just trigonometry. Recall if you have this set up like this. This is a theta, this is y. If you have the sine, again, just sine looks like this. This is at pi over 2. And this is sine. So at sine pi over 2 equals to 1. Yeah, like that. And then if we draw in red, and this is the cosine. Cosine starts at 1 and then goes down like that, peaks like that. Basically, it's opposite of whatever the other one is. And yeah, so it's something like that. And then, or like that. Anyways, and then this is our sine. I'll make this a bit better. It goes like this. Whoops. Yeah, and then goes down. Yeah, so anyways, this is sine, and that's at 0. This is, cosine. That's cosine. All right, so cosine theta is that, and then there's the sine theta, and that's at 0 is over there. I'll put a 0. So just red is 0, is 1, and we used 0 and 1 there. All right, yes, pretty epic stuff there. So I'll click this. Okay. All right, so now that we have the vector normal to the normal, so the normal vector, or vector normal to the normal plane, we could find the equation of the plane using recall from my earlier video on, there's a link to it, on the equation of a plane from the normal vector. So a vector equation of a plane, if you have a plane like this, a normal vector n, and then you have the position vector r, it's just up to any point, just x, y, z, so point P like that, and then this is the initial point P naught. That's the one we actually are starting off with. P naught is going to be our 0, 1, pi over 2. That's our P naught. And we go to just a generic one, x, y, z. And then basically the dot product, n, with the difference of this position vector, so from x, y, z, subtracted by this initial vector. The dot product of it equals 0, and then from there you can get the scalar equation of a plane, and so on. So thus an equation of the normal plane at P is, and basically instead of n we have this right here, r prime of pi over 2, which is -1, 0, 1, so that's the vector. So this equals to r prime pi over 2 dot product with, now we just take a generic point x, y, z on the plane. So, and this is going to be our, and then subtracted by the point there, starting point, that's on the curve. So 0, this is 0, 1, pi over 2. That's our starting point P. All right. And this dot product has to equal 0 because it's 90 degrees. So dot product is 90 degrees, it's equal 0. So this equals to, now if you take the dot product, again, this expand this out and then just simplify this. So this one right here, we already know this is going to be, that's going to be this, -1, 0, 1. -1, 0, 1. All right, so we got this. And then dot, and then we're going to have a x minus 0. That's just, I'll just put a, x minus 0 is just 1. We just subtract this. So x minus 0 is just x. So y minus 1. Put it like that. Y minus 1. And then z minus pi over 2. Z minus pi over 2. Like that. This equals to 0. And now multiply these inside. So -1 times x. Again, dot product, you just multiply each one and add them all up to get a scalar. So -1 times x is just going to equal to, this equals to negative x. And then now 0 times, this one here is just going to be 0. 0 times y minus 1 is just 0, so plus 0. And the next one's 1 times this right here, z, this is going to be plus z minus pi over 2 equals 0. All right, so we get this. And now this plane, I'm going to write this in terms of z. So I'll move this over to the other side, this over to the other side. So what we get, the plane is going to be equal to z is equal to x plus pi over 2. So this is the normal plane. So normal plane. All right, so now we got the normal plane. The next setup is we have to find the osculating plane. So again, we're asked to find the normal and osculating plane of the helix in example 6. So going further, so the osculating plane at P contains vectors t and n. So its normal vector is going to be, so that oscillating plane number, it's kissing the, or touching the surface. It's like kissing it. So it's going to be tangent. It's basically all the points that contain t and n. So its normal vector is the cross product. So in other words, normal vector is the, it's a cross product t cross n, which equals to b. In other words, that's the binormal vector. That's from example 6. So from example 6, we already have, so I'll go all the way to example 6 and I'll just copy that normal vector. So this is what we had. So I will copy this out. So that's our normal, that's normal to the oscillating plane. So I'll paste this right here, and again, example 6, we have it's the same helix that we're dealing with. So this is the normal. Yeah, so that's the normal binormal vector. All right, so that's our binormal vector, but we want it at the point t equals pi over 2. So at the point p, right here, 0, 1, pi over 2, as we did above here. So t equals pi over 2. So we just plug in t is equal to pi over 2. So we get the binormal vector at pi over 2 is equal to 1 over square root 2, and then plug this in, sine pi over 2, negative cosine pi over 2, and 1, like that. And where pi over 2, sine pi over 2, again, going back to that graph right here, sine pi over 2 is just 1. And then negative cosine pi over 2, that's just 0. So it just goes to 0. Yeah, so it doesn't change much. So in other words, we're just going to get a equals to 1 over square root 2. 1 over square root 2. This one is equal to, 1. And then this one's 0. And then 1. Yeah, so 1, 0, 1. And then if you multiply that inside, this would just equal to 1 over square root 2, 0, 1 over square root 2, like that. So that is the normal vector, except we don't actually need this 1 over square root 2 because it's just parallel to it. So we can just remove it, but we'll get that in a bit. All right, so if that's the normal vector, again, a simple normal vector is just 1, 0, 1. So an equation of the oscillating plane is, well, again, the reason that's simpler is because if we had a plane like this, and if we had a normal vector, so this is going to be, let's say our normal vector is like this, like that. So this is our normal vector b, or binormal vector. But then this is divided by 1 over square root 2, so it's actually smaller than the one we want. Well, it's a unit vector, so it's unit 1 there. But what we'll do is multiply this by square root 2, so that it's the same one but longer. So this is going to be this right here is going to be the binormal vector times by square root 2. So in other words, it is still normal. This is still, the whole thing is still normal to the plane, but it just equals to now 1, 0, 1. Because we got rid of all these, the denominator. Yeah, so that we just deal with that. So now we have that. Now we can find an equation of the oscillating plane using this setup as well. So we go the exact same thing. So we take the derivative, the dot product of the normal vector, the binormal vector, but with the exact same thing here. So x, y, z, point on this, subtract by our point P. All right, so now we take our normal vectors, our b there. So this equals 2, but then we're going to be dealing with multiplying by this square root 2. So, but I'll do that for completeness. I'll just do it for completeness. So a better one would just be this times by square root 2. Yeah, square root 2 times by our binormal vector, just to make it, it's still going to be yeah, it's still going to be normal to that plane. This is at pi over 2. Dot product with, and then again, the same exact thing, x, y, z, subtracted by our position vector 0, 1 up to our starting point, 0, 1 pi over 2. And then this equals to 0. So the dot product is equal to 0. And again, this times by square root 2, we could divide by it and divide by both sides. And it, again, the same thing, doesn't change anything. All right, so going further, this is going to be equals to, this is going to be 1, 0, 1, dot product with x, so x minus 0 is just that, and then y minus 1, z minus pi over 2, like that. That equals 0, then do the dot product, 1 times x is just 1, I mean just x, and then 0 times y minus 1 is 0. Yeah, plus, all right, plus 0. And then the next one is plus, again, it's be z, yeah, z pi over 2. So it's exactly the same equation we had, except instead of negative x here, we have positive x. So again, if you go back to the earlier one, we showed here is negative x, and move it over, we get this x plus pi over 2. But now we have a positive x, so then the actual equation will be negative. So we move this over to the other side, move this over to the other side, we're going to get a z is equal to negative x negative pi over 2. I mean plus pi over 2. Like that. Yeah, and it's plus because this is plus, move it over, it becomes, I mean this is negative, move it over, becomes plus. This is plus, move it over, becomes negative. And this is our osculating plane. All right, so epic stuff there. All right, and yeah, going further here, so the figure below shows the helix and the osculating plane in example 7. This is from a calculus book, and yeah, basically you can see how it's kissing the curve. So in other words, it's right on it, like that. Yeah, it's literally touching it. It basically contains all the points near it or closest to the point P. There is basically like just putting a piece of paper right next to the curve. Yeah, so this is the plane. Z equals a negative x plus pi over 2, and it looks like that. That's pretty interesting. And for reference, here's a graph using GeoGebra. Yeah, so we have that same setup here, and then basically as before in example 6. But now we have wrote the osculating plane, Z equals negative x plus pi over 2, and the normal plane, Z equals x plus pi over 2. And again, you can see this in blue is the osculating plane. So it contains a tangent vector, n. And then the binormal one is the normal one, contains a normal and binormal. So it looks like that. So it's pretty cool there. And again, it goes through all space there. And you can move it around there. And this is off from there because this is I have it changing. I didn't make the other one variable, but this one you go to pi over 2. So or a or our pi, I mean, or our t is like that. So pi over 2. So there it is. At pi over 2 equals that. Then if you just make it generic, so 1.57 is pi over 2. So a, just make it generic so you can move this around and go to all the way 1.57. It goes over there somewhere. Yeah, so yeah, absolutely fascinating. And again, I'll put this as pi over 2. Pi divided by 2. And yeah, you can see that there. And you can see the tangent vector and the plane is right on it. And there's a normal vector and the normal plane and the osculating plane. So it contains pretty much all those points on there. Yeah. So pretty fast. And the normal one is pretty much normal to it. Osculating is literally like kissing it. So amazing stuff there. All right, I'll move this down like that. So now let's go further and I'll look at osculating circle. So the circle that lies in the osculating plane of C at P has the same tangent as C at P, lies on the concave side of C towards which end points. Basically, yeah, we're end pointing always to the z-axis, as I at least example showed. This one's going to be this. No, instead of that, we're going to be dealing with a circle. And the reason is because the radius circle right here, we'll call this the radius rho. Yeah, radius rho is equal to 1 divided by the curvature. And that's the reciprocal of the curvature. So again, when you have the circle, you can basically see how much the curvature is based on the radius. So that's a cool thing about the oscillating circle. And you can see example 3 when I proved that. And I'll scroll that now just because it's been a while since example 3. All right, yeah, so we're back here. So curvature of a circle is 1 divided by radius. And then basically I showed that the circle has the curvature 1 divided by a, where a is radius. So that's quite fascinating. All right, yeah, so basically recap again. So the circle that lies in the oscillating plane of C at P has the same tangent as C at P, lies on the concave side towards N, has radius rho equals to 1 divided by the curvature, and is called the osculating circle, or the circle of curvature of C at P. It is the circle that best describes how C behaves near P. It shares the same tangent, normal, and curvature at P. So it's quite an interesting visual demonstration of curvature. So we'll go over here the last example, example 8 of this extremely long video. So example 8, osculating circle of a parabola. So we're asked, find and graph the oscillating circle of the parabola y equals x squared at the origin. So solution. So from example 5, the curvature of the parabola at the origin is kappa equals to, kappa of 0 equals to 2. And we could quickly scroll all the way to example 5 and to show you that. This is the example 5 right here. So this is that parabola. So at the origin of this parabola, y equals x squared, at the origin, the curvature was 2. So that is there 2 there. Yeah, and since we're asked at the origin, so if the curvature is 2, that means radius is going to be, of the circle is going to be 1 divided by 2. So the radius is 0.5 or 1 over 2. So as per example 3, the radius of the oscillating circle at the origin is 1 divided by kappa, which equals 1 divided by 2. And its center is going to be, well, the origin, and then the basically the origin, basically 0, and then basically this part right here is the top part, which is the center is going to be at 1 over 2. So that's the curvature, or the radius. So 0, 1 over 2. Its equation is therefore, so if the center is 0, 1 over 2, and recall the equation of a circle, this is just going to be x squared plus, because it's the x is at the origin, and then the y is going to be shifted up. So we have put a 1 over 2, you have put a minus 1 over 2. That's because to get y to the origin, you would need to plus 1 over 2 to get it back into basically the same reference frame, whatever that's called. So to make it equal to where it is the origin, y, to make it, for example, x, when you plug in 0, it just becomes 0, but to get this to be 0, you need to put y as 1 over 2. So in other words, it starts off at y equals 1 over 2. Anyways, this equals to the radius squared, and the radius in our case is 1 over 2, so 1 over 2 squared, this equals to 1 over 4. So that is that, All right, going further. So again, a quick recap from my earlier video on the equation of a circle. So equation of a circle, and equation of a circle with center h and k. It's going to be equal, and radius r is equal to x minus h all squared plus y minus k, then that squared equals r squared. In particular, if the center is the origin 0, 0, then the h and k vanish. We get x squared plus y squared equals r squared. So anyways, so for the graph in the figure below, we use parametric equations of this circle, and we can obtain this actually. So if we have, what I'll do now is, because Calculus book didn't actually draw this, so we're gonna have to make a good circle. So what I'm gonna do is, I'm gonna draw this like this. I'm gonna draw this x, this is the y, and now I will just plug in the circle. So we go like this. Where's the circle? Draw circle is gonna be somewhere, insert shapes, pictures. How are you supposed to find a equation? Nope, this is drawing. All right, yes, shapes. So drawing shapes, circle. I'll put it in like this, and if I press shift, it makes it. I think it makes it like that. Okay, so it makes it. Yeah, so that. Whoops. I'll put that again one more time just to show you guys how I do this. Yeah. Okay, so we have the circle there. I'll make this a bit smaller. All right, so we have a nice looking circle. All right, so a nice looking circle like that. And because again, Calculus book didn't draw it, so we can't just use theirs. All right, so we have that like this. So there's our circle, and it's going to be starting at this top part. This is this radius is 1 over 2. So 1/2 like that. And then, so to get the parametric equations, we're going to basically shift the origin up top there. And let's say we have a point here. And this is the height there. We'll call this h. We'll call this x, because again, x from the origin, we use x. And then this is, this right here is the hypotenuse. and the radius is going to be one half. Yeah, so hypotenuse is 1/2. And now the y is going to be this full height. So the point here is going to be our x, y, the coordinates. But the full height is going to be y equals 1/2 plus h, like that. And again, using basic trigonometry, and then where we have the t is like that. So we'll have the t is the angle between this triangle. Yeah, so that's our t. And then basically we have cosine of t is equal to, well, adjacent over hypotenuse, so x over 1/2. Yeah, x over 1/2. Yeah, so in other words, yeah, we have x over 1/2, and then sine of t is equal to, well, h, opposite over hypotenuse, 1 over, yeah, over 1/2, like that. So that's what we have there. So then our parametric equations are, well, x, move this over to the other side, so x equals to 1/2, move this over 1/2 cosine t, and then y is equal to, well, 1/2 plus h, where h is equal to 1/2 sine t. 1/2 sine t, like that. All right, so now that we have these parametric equations, well, we can plug that into GeoGebra, but before that, I'm going to just graph this manually. So what we end up having is, if we graph the parabola like this, so the parabolas, and then I'll use the calculus book screenshot, is y. So we have the parabola like this. I'll fix this, just make it a bit not so wild. All right, just fix this up. It goes like that. This is the parabola, y equals x squared. And then we have now the osculating circle. It's going to be like this. This would be at 1/2. It's going to be like this somewhere. Yeah, so that's going to be our oscillating circle. And this is our osculating circle. Yeah, so that's how it's going to look like. And what I'll do is I'm going to pause and replace with the screenshot. All right, so here is, here's a screenshot to replace my drawing with this one. And also, if this is 1/2, so then the radius is going to be, well, reaching up to 1/2 here. And then there's the 1 there. So there's the, if you make a cube. So that's pretty interesting. And again, this is the same curvature right here. So at 1/2. So you could think it visually as the curvature, you could put a circle in there. And it touches this part here. It's tangent to it. It's the same tangent, everything tangent across, and so on. And yeah, and basically, the curvature is 1/2. The curvature is 1 divided, the radius is going to be 1 divided by the curvature. Yeah, so the curvature is 2, So the curvature is 2. So the curvature is 2, the radius is 1 divided by the curvature. So the radius, this is going to be the curvature. Yeah, curvature is that. So that's pretty fascinating. All right, so to continue further, for reference, here's the graph using Desmos, the 2D graphing calculator, including showing how the osculating circle changes as a point moves along the curve. And note that I used Grok AI to obtain the general osculating circle equation, just because the calculus book didn't cover it in this chapter, and it's don't want to spend another few hours proving how to obtain this one. But basically, this is basically we have the y equals x squared. We have the equation of our osculating circle for the case of t equals to pi over 2, and that's at the origin. So basically x squared plus y minus 1/2 all squared equals to 1 over 4. And then so what I did also was I put a general point a and a squared. So basically a for x and then a squared for the y. And then this one here, I didn't share it, but I just put it there because I was trying to make a formula. Then I realized it's actually wrong because if you graph, what I did before was I just replaced the radius, the radius there with a squared. So instead of going 1 over, instead of going r squared, what I did was 1 over a squared, and then you get interesting results, but it's actually wrong because the oscillating circle is always supposed to be pointing in the within the curve, like always in the normal direction. So as you stated in this part here, so it basically, so it's a circle that best describes how C behaves near P. It shares the same tangent, normal, and curvature. So it has to be the same tangent, normal, and curvature to be called osculating plane. So so that's when I realized my equation was wrong. So then I just asked Grok, just make it for me. and it made me this giant equation there, and I'll show you how it works. So right now, it's in orange. This screenshot's in orange. It matches up with this one here because it's at the origin. So it matches up like that. And then when you move it over, so notice here, it's tangent. It's tangent there. It's pointing in the normal direction. And it has the same curvature. So this has the same curvature, and that's the radius of this is the curvature. So this circle is pretty amazing. And then notice how the one in the blue is the one that's just a static one at the origin. That is just our basic circle equation there. And we'll open up the Desmos calculator to show you this. It's pretty amazing. So first of all, here's the, I asked Grok, make me a Desmos thingy. It said a bunch of stuff, and I'm like, okay, just give it simple one line. There's the one line right here, and just plug that in. You can copy and paste this line Desmos, and it will work as needed. And I think this also this also makes a fraction or something. But anyways, copy either or play around with it. I put a link to it anyway. So here it is. So what I'll do is I'll go to the origin. So notice if you go to the origin, it matches perfectly there. So perfectly at the origin. So I'll unhide this, and there's the origin. That's the static one. And if I click this one, remember this one from our example 5, there's that one goes up to 2 and goes back down. And then because this is the curvature, actually keeps the radius is 1 divided by the curvature. Yeah, so keep that in mind. So this is the radius is 1 divided by the curvature, the k, not the other way. I keep getting that mistake. So basically, this large circle means this curvature is small. So I'll keep this graph there. So as you make this bigger, and I'll show this one. Yeah, as you make it bigger, the curvature gets smaller, but the circle gets really, really big, and then as it pretty much lines up with it, and look how big the circle gets. And that's because this is dividing by a super tiny number. Yeah, so that's quite fascinating. And I think I'll put that screenshot instead, actually. So I'll do this screenshot like this. And yeah, this is pretty cool, actually. So what I'll do is I'll take this screenshot and take it like that. Yeah, so basically the curvature, as it gets small, the osculating circle gets large, and also it's always tangent to it. So it's a pretty cool equation there. So we'll put this, I'll remove this just to illustrate, just to drive home the point. Large circle means small curvature, because it's basically a straight line now. There's very little curvature, just basically a perfectly straight line there. And so on. So that's why small curvature. This one has big curvature, and that's why it goes up over the 2, and the circle is the smallest over here. All right, that's fascinating stuff. So let's continue further, and let's take a quick look at the summary. And I'm going to just make this better. Yeah, so summary of T, N, B, and K, kappa. So the tangent vector, normal, binormal, and curvature equations or formulas. Yeah, so we summarize here the formulas for unit tangent, unit normal, and binormal vectors and curvature. Yeah, so so basically everything there. So all the equations of those. All right, so the unit tangent is going to be like that, capital T. This equals to like this, of T is equal to the derivative of the vector function divided by the length of that derivative of the vector function, R of t, like that. So that is R of t. So now the normal, so that's the unit tangent vector. All right, I'll put the unit normal vector is going to be like this. This one is equal to the derivative of the unit tangent vector divided by the unit tangent vector length, or the magnitude. All right. And now the binormal. And here I'll quickly just pause it and shrunk and move them all in one line. I'll put the binormal as well, just I don't want to make it too big. So binormal of t is equal to, and this one is just going to be both those cross product with each other. So this is t and the tangent vector cross product with the normal vector. So that's the binormal vector like that. All right, here I just quickly shrunk that all inside there. So that's that. And then finally, the curvature has a bunch of these. So the curvature is kappa. This equals to, well, by definition, was the length of the derivative of the, this is going to dt over ds in terms of the arc length function. This is the derivative of the unit tangent vector in terms of the arc length function, and that's from the beginning. I'll scroll the way back up. Yeah, I'll just scroll up. I'll just teleport. I'll pause the video and go all the way. Alright, here I teleported, and it's not the beginning of the video, but beginning of the curvature section. Yeah, so the curvature of a curve is defined as kappa is equal to this right here, the length or the magnitude of the derivative of the unit tangent vector in terms of the arc length or arc length function there. And then afterwards, I showed that that's actually easier just to use this formula instead. So use it in terms of t. So it becomes this right here, the length of the derivative of the unit tangent vector divided by the length of the derivative of the vector function. Yeah, so that's the part. And then afterwards we get the one with the double, this one here. We get this a cross product, which is more convenient, and that has the first and second derivative, and there's the cube function there. So let's go all the way back down and write these out. All right, and we are right here. All right, so we're back here. So this equals 2. So we wrote that in the more convenient one, this is this right here, like this. The derivative of the length of the derivative of the unit tangent vector divided by the length of the derivative of the vector function, like that. And then this all equals to the cross product, or the length of the cross product of the first derivative of the vector function cross with the second derivative of the vector function, all divided by the magnitude or the length of, this is going to be the length of, this is the the first derivative of the vector function r prime of t, then cubed. All right, so we got all that. So that's kappa, and there's the unit tangent. This is a unit normal. This is unit binormal. Again, I say unit just because they're all unit vectors. And then we have the curvature. So yeah, so that is all for today. Yeah, so that's quite an epic long video, and hopefully you enjoy this. And I'll scroll the way back up and do my usual chit chat as I scroll up this giant piece of notes here. And again, I'll be uploading all these in the notes. I'll be uploading the notes in article format, PDF format on the Hive blockchain, and I'll also do sections, and then mainly to do the thumbnails, because thumbnails basically help me memorize what I did, and very easy to share, and so on. And I'll be doing sections throughout the coming year, and so on. And I'll try to be uploading more of these videos more routinely, just to get my brain get used to doing math videos, and also just get these out there. A lot of people learn a lot from this. Anyways, so hopefully you enjoyed this, and I do need a new Surface Pro. This one's a bit slow. I got a new Mac, first time ever having a Mac, and it's super fast, but this computer is just a bit slow. But this one's PC, but it's super old, this one. And it just it's a bit of lag, because I'm getting used to the Mac has 0 lag. It's just a bit weird to use it, but 0 lag. This one has a bit lag. It's not used to that. Anyways, that's all for today. Thanks for watching, and stay tuned for another math easy solution.